thought-provoking discussions and innovative ideas. We are absolutely exhilarated to dive into another day of learning, collaboration, and groundbreaking innovation.
To begin today's proceedings, we have with us the guest of honor, a visionary in the field of critical metals, Professor Chaitanya Moy Ganguly, President of Critical Mineral Association of India.
Dr. Ganguly has been a guiding force in promoting indigenous expertise and fostering global collaboration in critical minerals. We are honored to have him with us today.
Now, with immense pleasure, I would like to invite Dr. Chaitanya Moy Ganguly on stage, and I request Professor Dheeraj Kumar, Deputy Director, IIT ISM Dhanbad, to kindly escort him onto the stage.
Please welcome them with a round of applause. To do the honors of introducing and welcoming our esteemed guest, we would like to request Professor Dheeraj Kumar, a person of profound vision and our guiding force, to decorate him with the floral bouquet. Yes. Kindly come to the center of the stage, sir. We now request Dheeraj sir to introduce our chief guest to the gathering and give a few words about it.
Padma Shri Professor Dr. Chaitanya Ganguly ji, my dear colleagues from IIT ISM Dhanbad and from other part of the country who are present over here in this particular special program of the conference. It's my immense pleasure to introduce before you the guest of honor of today's function, Professor Dr. Chaitanya Ganguly ji. As name suggests, Chaitanya. Sir, the Supreme Spirit is the Chaitanya. And you can understand when I talk about Supreme Spirit in which area? Supreme Spirit in critical mineral. So he understands the criticality of exploration, he understands criticality of mineral processing and recycling. And it's not only his understanding, he has all practiced over almost 50 plus years. And still you see a man of more than 80 years old, and still he is so active. We made a request just few days back that, sir, if you can honor us by being in IIT ISM Dhanbad and on a special occasion of a conference on critical metal, the first conference we are organizing on critical metal, if you can be here in the campus, he readily accepted our request. So with this few words, let me introduce officially Dr. Professor Chaitanya Ganguly, the founder president of Critical Mineral Association of India. He is well known in nuclear and material engineering community in India and abroad for his pioneer and outstanding work. That too in the area of uranium, plutonium and thorium-based ceramic, nuclear fuels, industrial production of uranium oxide fuels for operating water-cooled nuclear power reactors in India, and indigenous development and production of high density more than 5.2 gram per cubic. Not only that he worked in industries, he worked in R&D labs, he has also been into academics. He has been distinguished professors at IIT Kanpur and other places, and he also holds many fellowships. He holds a fellowship of IIT, INSA, IAS, and many. We strive to get at least one fellowships, and he has almost 3-4 fellowships of national fellowships. It's not a sort of a small fellowships, but national fellowships. He has been instrumental in working in DAE, served for more than 35 years, and retired as a distinguished scientist, the chairman and chief executive of Nuclear Fuel Complex NFC and Industrial Unit of DAE at Hyderabad. He started his career in Radio Metallurgy Division of BARC, DAE Mumbai, and played a key role in setting up the plutonium fuel laboratory and had developed, manufactured the untired plutonium rich mixed uranium, plutonium carbide advanced fuel for the operating fast breeder test reactor in Kalapakkam. He was head of the radio metallurgy division, worked for several years before joining the CSIR Glass and Ceramic Institute, CGCRI at Jadavpur, where he was also heading, he became the director of that particular CSIR lab. From CGCRI, Dr. Ganguly moved to this NFC, Nuclear Fuel Complex in Hyderabad, as chairman and chief executive. He could turn around the NFC into a leading nuclear fuel and ferrous and non-ferrous tube fabrication plant in the world. Dr. Ganguly then served the International Atomic Energy Agency also at Vienna as head nuclear fuel cycle and material section for 5 years. Then he joined Camco Corporation Canada, the largest uranium and mining fuel service company in the world, as President Camco India office. Yesterday in the evening, I had a brief interaction with him, and the way he narrated his entire career in Canada and other places, and how the leaching and other processes was implemented in his sort of leadership was phenomenal. He is a distinguished alumnus of IST Sipur, the erstwhile B College Sipur. In the last 12 years, Dr. Ganguly is actively associated with academic stations, as I told you earlier also. First, he served as a distinguished faculty member, visiting professor at IIT Kanpur, followed by he was advisor to Director General, a distinguished professor and mentor of Department of Nuclear Science and Technology at the Pandit Dindal Energy University, Gandhinagar, Gujarat. He has authored more than 250 research papers and has been also guiding MTech scholars, PhD scholars at IIT Mumbai, then University of Mumbai, IIT Bangalore, Osmania University, and so on. As I already told you that he is holding the fellowship of NASI, fellowship of INE, fellowship of IAS, and also the Indian Institute of Metal and Indian Institute of Ceramic at Kolkata. He is also recipient of National Metallurgical Award by the Ministry of Steel and Mines, the Tata Gold Medal Awards of the Indian Institute of Metals, the Material Research Society of India Medal, the Pacific Science and Technology Award, the Distinguished Alumnus Award of B College Sipur, the Lifetime Achievement Award of the NDT Society of India. He was one of the first to receive the Indian Nuclear Society Award from the Honorable Prime Minister of India in 2001 and was confirmed Padma Shri, the second highest honor of the country in 2002. He is the founder president of Kit Cabinet Association. Ladies and gentlemen, please have a round of applause for Professor Dr. Ganguly. So with this brief introduction, sir, your list of success is quite long. I request you to have your word of wisdom to all of us.
Namaskar. At the outset, I must thank Professor Dheeraj Kumar ji and Professor Lalish Kumar ji for inviting me, and this is a unique opportunity for me because I am visiting Dhanbad for the first time in my life. My nephew is a graduate from this college. His name is Samik Chattopadhyay. He is now a big shot in one of these consultancy. He's a geostatistics by profession and also in exploration. So what I propose to, first of all, I would like to congratulate you because I was told that ISM will be, this is the centenary year of ISM. It's one of the old institutions in the country. I also graduated from B College, where my grandfather also graduated from the same college. You can just imagine, it's nearly 200 years old. So BHU, B College, and I would say Roorkee, these are the three main engineering colleges old time, and IITs came much later. I had the unique opportunity to work hands-on. I mean, whether it is in the field of research and development or in the industry. So I would share all my first-hand experience, particularly in the area of uranium, thorium, and plutonium. Plutonium, as you know, is not available in nature. It's a human-made element obtained from U-238 that occurs in nature. And as you know, plutonium is a strategic material used for nuclear weapons and also for civilian nuclear application. So I had the unique opportunity to work in both areas. In fact, we are the first generation plutonium metallurgists of India, which are responsible for setting up the plutonium laboratory in radiometallurgy division under the leadership of my boss, late C.P.R. Roy. And then, of course, we could do all kinds of work on, mainly based on powder metallurgy. Then I moved to nuclear fuel complex. That gave me a unique opportunity. Many of you are not even aware that nuclear fuel complex is perhaps the only unit under one roof. You have zirconium technology, you have uranium technology, you have special material technology, and all kinds of tubes you can think of. It is one of the largest tube manufacturing plant, particularly tubes and pipings that are needed for the strategic sector, defense, atomic energy, and aerospace, all kinds of materials. So I would say, so far as this critical minerals are concerned, my specialization is more on the back end, not in the upstream, not on the exploration. But I have a lot of respect for the geologists and also the mining engineers. And the mining engineers, they hand over the concentrate to us, and then thereafter we take over and make the final product and recover. After the material is used up, we try to recover the valuables like uranium and plutonium and recycle. So what I will do, I will give you a typical example of uranium fuel cycle, which should be, in my opinion, a role model for all critical materials, because you have to, when you talk about the life cycle management of critical minerals, not only in the front side, but you will have to recover these materials, because it is very difficult to get lithium. You are importing lithium. So whatever is produced in the lithium ion battery, after use you should be able to recover the lithium, the cobalt, nickel and phosphates and recycle it back in the reactor. We are in the era of recycling. Even in the academics, we had one innings and now we are having the second innings. That means you are recycling the system. So it's in recycling system. You go for steel, for instance. Nowadays you hardly find steel made from pig iron. It is mostly scrap melting and recycling. Paper, most of these things are, so we are in a recycling era, and critical minerals are no exception. Now first of all, we must know what is sustainable development. Sustainable development means you enjoy whatever nature has given you, you enjoy. But make sure that you don't leave the waste for your next generation, for your children and grandchildren. You should make the world better. Yesterday I was visiting, on the way back I saw Maithan dam for the first time. It's such a beautiful thing. And when I went for a cup of tea and saw downstairs, it's full of plastic bags and dirts. And so I said, what is this? And it's the, all good places you have this. So the sustainability means whatever you have in nature, enjoy it and leave something for your next generation to enjoy, if not in a better condition. To give you an example, coal for instance. Okay, you have used coal extensively and coal has become a bad word now. But remember, coal is the mother of the Industrial Revolution. I mean, way back, James Watt discovered coal. And then you go to petroleum product in USA. That led to the diesel and kerosene and all these things, and that led to immense amount of prosperity in Europe and in the Western world. So coal is, we should treat coal with a little bit of respect. Maybe the coal use is over, another set of energy system will evolve. And then self-reliance. These are the two words which are very important for critical minerals. Self-reliance. Self-reliance does not mean that you will have to do everything yourself. No. So you develop the capability. Suppose if you have to have lithium, so you develop the capability of extracting lithium from the brines or from the rocks, like a spodumene sort of thing. But it's not if the cost of that development is pretty high, and if you can get lithium, imported at a cheaper rate, then you better import. So that will give you the buy or build option. So you develop the capability and build the capacity. Whatever you have developed, you have to build the capacity, and that is the new definition of Atmanirbhar. Because in a world, it's a global village. We have to share. I can again give you the example of uranium. You'll be surprised to know that more than 60% of the uranium are in countries which do not have any nuclear power plant. Australia, for instance, the largest reserves of uranium in Australia, followed by Kazakhstan, Niger, Namibia. Then you have Uzbekistan. So these countries, they do not have any nuclear power plant, but more than 60% of the uranium are in their countries. Simultaneously, if you look at France, they have 72% of their electricity from nuclear power plant, but they do not have a single gram of uranium in their soil. So importing, exporting, it's not a bad word. I mean, as if by Atmanirbhar you mean that you will have to do everything yourself. No, it's not needed. But you must develop the capability. Suppose if someone denies you that technology or denies you that material, you should be able to either find a substitute, alternative, just a lithium. If lithium-ion battery is expensive, if lithium is only 20 parts per million, so you'll have to find a substitute for lithium. So maybe I would say sodium-ion battery could be a better substitute. It may not be as efficient as a lithium-ion battery, but okay, that's a better alternative. So this is the definition. So based on this, whenever we are talking about critical minerals, we will have to keep in mind sustainable development and self-reliance. Now these are the main things for high human development. One is the energy security and environmental protection. Why energy security? Because energy is the engine for growth. Energy security will also pave the way for food security, fuel security, electricity 24/7, and also water security. That's very important. So energy security is most important. And then at the same time, while arriving at energy security, you should make sure that you protect the environment. Environment means clean air, clean water, clean land. Out of the 10 worst polluted cities in the world, 5 are from India. Can you beat it? So this is just not acceptable, because ultimately, so clean air, clean water and clean land, most important. And then minimization of CO2 emission. All of you are aware, the CO2 is a greenhouse gas, and that's a stable greenhouse gas. Ek bar release ho gaya, it will be remaining in the environment for tens and thousands of years. And then the other greenhouse gas is methane, which has got 20 times more effect than CO2. But the lifespan of methane in the environment is about 12 years, not so bad. So one has to take care of minimize the CO2 emission and methane and NOx in order to keep the global, we have made a commitment, the global commitment is that due to the United Nations framework of climate change, that we will not allow global warming to exceed 1.5 degrees Celsius. So very important. So there is a mad rush for decarbonization in electricity generation, cooking and transportation. I remember childhood days, I think I'm the only guy born before independence. So you can imagine the type of hardship we saw. There used to be a ration card up to 1970. Everyone was running after the ration card and all things. But today we are one of the largest producer of food grains in the world. When I was there, the entire population of India, Bangladesh and so-called Pakistan combined was 400 million. Today we are 1600 million. So just imagine the challenge to feed this 1600 million people is no joke. And today we are having bumper crops. Food grains, I would say cereals, pulses and oil seeds. We are one of the largest producers in the world, of course next to China. So these are some of the things we have achieved. During independence, the total installed electric power in the country was 1500 megawatt, only 1500 megawatt. Today we are nearly 500 gigawatt. So it's a fantastic achievement. But even then, because of the area population, it is not adequate. We will have to increase by a factor of 3 in order to have a per capita consumption of electricity in the range of 4 to 5,000. I will come to that. And then of course, our target is zero emission. Now, the most important thing is waste management and wealth from waste. We will have to find out a mechanism of evaluating the most important components from waste, all kinds of waste. Nuclear waste, I would say, you can take the e-waste is most important. And in the e-waste, mainly recovering, and suppose the magnets, you have the neodymium, you have the samarium, you have the praseodymium, dysprosium, and also, so you will have to find a mechanism for recovering them and recycling them back into the system. And these are, I would say, that means recycling and wealth from waste. Same with agricultural waste, industrial waste, and municipal waste. So critical minerals, when we talk about critical minerals, you will have to keep these things in mind. Number one, to make sure we have energy security. Number two, the focus is on carbon-free electricity generation, carbon-free transportation and cooking. And then we will have to take care of the environmental protection, both in terms of, I would say, greenhouse gas emission and also waste recycling. Next slide, please. It's not working. So I'm sure all of you are familiar with this so-called 30, it's not 30, it's more than 30, because rare earth element 17 they have considered as 1. Platinum group there are 6 they have considered as 1. So anyway, 30, fine. It's the wisdom, collective wisdom of the team of the Ministry of Mines who suggested this. And this gives you a picture of, this gives you, go back please. Could you? आपका पॉइंटर भी काम नहीं करता, लाइटिंग चेंज करो। हाँ, तो क्या कर लिखा? You see, I am an old school teacher, chalk and blackboard. अभी these are, so you give me a stick, I should be able to get. So you see, these are the minerals, and the focus, I would say, mainly, there is a lot of hue and cry all over the world on lithium and rare earths. Say, dono abhi buzzword ho gaya. Even they're thinking of continuing the war, the Russian-Ukraine war, or the, I would say, Balochistan and all these places, mainly to grab the rare earth. And you know, lithium also, as you know, it's only in the ABC countries, Argentina, Bolivia, Chile, and then these are the brine, and you have the rock from spodumene in Australia. And the Chinese have managed to grab most of these things, and they, in Australia and all these places, South American countries, they just collect these things, concentrate it. Australians don't even concentrate. Directly they do the crushing and send the whole thing to China for a cursor. Yeah, that's good. So you can see this gives you then an idea about the occurrence in nature. So as you go to the pink color, that means they are abundant in nature. For instance, I should focus on the materials that are abundant in nature. You see the entire steel industry, it is based on iron. And you can see sodium, silicon. This is the basic raw material for the solar photovoltaics. But the most unfortunate part is not a single gram of polycrystalline silicon or silicon single crystal for photovoltaic application is produced in the country. We don't even produce metallurgical grade silicon, you know, silicon. You start see, silicon is the second largest element in nature after oxygen. So we have to make full use of whatever silicon you are having, even though the efficiency efficiency of the solar cell is in the range of 18 to 20%, and alternative solar cell material have come, cadmium based, telluride based, and also the perovskite. But it is better to stick to the silicon thing because it is available in nature in plenty, and you can make large amount of the solar cell. So this is very important. And then you can see they have, as I told you, the focus is on the lithium-ion batteries in the transportation sector, mainly to minimize the CO2 and the methane emission. And then you have also the rare earth magnets, particularly the rare earth magnets. They are permanent magnets, mostly the neodymium, iron, boron, and the cobalt, samarium. I think we have experts, Panditji like Ranjan Kumar, will be presenting something. I'm looking forward to listening to you. And then the most, for me, the biggest challenge is after use, how do you recover the neodymium, how do you recover the praseodymium, how do you recover the selenium and recycle back into the water. That's the biggest challenge. And then downstream, when you are making these magnets, because this is a magnetic material, the magnet, they need a particular orientation. So the compaction has to be done under the appropriate magnetic field. To the best of me, please correct me, I don't think we have really industrial scale operation for producing this neodymium, samarium and cobalt. Now of course they are starting, and also to processing in the form of magnets and final use. Most of these things, nearly 100%, is imported from China, and the China, they are prepared to set up the plant. Some of our colleagues from the Critical Minerals Association of India had been to China. They are prepared to set up the plant in India, but the government of India is not encouraging such things, and rightly so. And then of course, for the defense material, most important thing is niobium, hafnium, titanium, nickel, tungsten, and zirconium. Zirconium is for nuclear mainly, but these are the things. And for that purpose, nuclear fuel complex, we have a special material plant. And this is not, the word critical minerals have come, I would say 5 to 10 years. This is from very inception of nuclear fuel complex in the 70s. This special material plant was set up mainly for tantalum and niobium extraction from the pegmatite, wastes. And then also hafnium. It's a byproduct. Hafnium and zirconium occur together. All zircon sand will contain about 1.5 to 2% hafnium oxide. So you recover the hafnium from the raffinates and then recycle them in the form of materials which are used for the nozzles in the reactor. And recently, Dr. Narayanan, who is the boss of the Department of Space, he visited. That was in July in this month, this year. And then we handed over this niobium. During my tenure in NFC also, we worked on the separation of tantalum and niobium. So this hafnium, niobium, vanadium and titanium alloys, these are being processed in the form of tube in NFC for this thing. Unfortunately, in the critical minerals that are identified intentionally, I think they have kept the actinides out. They have kept uranium out of this thing. And I don't know what is the reason behind. Srinivas also shares with me why uranium has been kept out. Because you see, uranium is, whether you like it or not, it is going to play a very important role. Nuclear power is going to play a very important role in the future. The government of India has announced installation of 100 gigawatt nuclear power by the year 2047. Today we are only 8 gigawatt. So you have to 12 time increase in that. I don't know how it will be possible. And we do not have enough uranium in the country. So we will have to import. Right now also, more than 60% of the uranium is imported, mainly from, I would say, Kazakhstan and Canada, and also Russia, and a little bit from the French colonies in Niger. Now they're planning to get it from Uzbekistan. So in my opinion, uranium should also be listed in the list of critical minerals. And as you know, uranium has got two isotopes, U-235 and U-238. The U-235 undergo fission in the reactor, produces huge amount of energy, which you convert into steam and then run a turbine and produce electricity. The fission also produces neutron, sometimes 2, sometimes 3. 1 neutron you need for sustaining the chain reaction, and the extra neutron interacts with U-238, which is 99.3%, and gets converted to plutonium, which is a human-made fissile element. And then part of the plutonium, it undergoes in situ fission and contributes to the energy and remaining remains in the fuel. So hardly in the present generation of reactor, only 1% of the uranium is used, and nearly 95 to 96% of the uranium and plutonium are in the spent fuel or in the used fuel. So we have to, reprocess, recover the uranium and plutonium and do multiple recycling. And let me share with you, whatever uranium has been identified in the world today, about 8 million tons. With that uranium, if it is properly used in water-cooled reactor, followed by fast breeder reactor and multiple recycling, then you can meet the entire energy requirement of the world for tens and thousands of years. And uranium is only 3 parts per million in nature, and thorium, which is the other nuclear material, is 3 times more in nature. I have not counted the thorium at all. Just uranium alone can meet this, and whatever uranium has been discovered so far. And I am taking only the uranium from the conventional mines. Unconventional source of uranium like the rock phosphate shales and all those things, they are again another 22 million tons. So sky is the limit, and we cannot ignore this. So far, the uranium has been contributing to nearly 9 to 10% of the global electricity. And in India, a country like India, we need this very, very badly, because uranium and nuclear power reactor is the only source which gives you carbon-free source, which gives you high base load electricity. Wind and solar, because the capacity factor is pretty low. Of course, with energy storage, the capacity factor will improve. But then coal and nuclear, they are only having high base load electricity. So I would suggest that the coal-fired station, when they are retired, the same location can be utilized for installing nuclear power plant, so that you can use the infrastructure, you can use also the power distribution system, and because acquisition of land is a big, big challenge. So that's the way progressively up to the year 2070-80, coal should continue to play a dominant role. As far as I'm concerned, I would say coal is a temporary critical mineral. There was a paper yesterday in the morning, someone was talking about, about coal also considering. I personally think that coal is a temporary critical minerals till we pick up on the solar and wind and hydro and other renewable and also the nuclear in a big way. So this is something which I would like to share. And then one of the other big challenge of the critical minerals is, one, as I told you, sustainability of the energy security, environmental protection, hygiene, and the most important thing which I would like to highlight is your national security. As I told you, national security is very important. We are planning to have a $30 trillion economy by the year 2047. At the same time, you should have very high national security, and national security in terms of nuclear weapons, in terms of nuclear submarines. So these are equally important area, and uranium is the basic raw material to have the so-called, I would say, your national security. Apart from whatever you are making for the Air Force and the defense and other places, all kinds of BrahMos and other kinds of missile material. And surprisingly, many of you may not be aware at all that most of the piping material for these things are made at Nuclear Fuel Complex in Midani. We have very close contact and collaboration, and we are supplying this material to the Department of Space and also to the Indian Navy. The Indian Navy, the entire indigenous submarines, Arihant and Arihat, most of the components are manufactured at Nuclear Fuel Complex in Hyderabad, including the climbing tube, the core structural material, and many of the private companies like Larsen and Toubro, Bharat Forge, they have contributed enormously towards this national security that we must recognize. So this is more or less in a nutshell about the critical elements. Next slide, please. So now we have formed this Critical Minerals Association of India, registered in Hyderabad. Again, I would request Ranjanji to become a member. You should become a member of the Critical Minerals Association. Many of you, those of you who are not members, I would earnestly request. I was thinking Professor Dhiraj and Professor Lailesh Kumarji to have a center, to have a chapter in your institutions on critical minerals. And you can see most of us are, Srinivas, please stand up so that people could see. We are from the atomic energy, many of us have come here to attend, and Srinivas also is coming to School of Mines for the first time. This was the first visit like me. and he is a very important player so far as the front end of this thing is concerned. All critical minerals is concerned. So this is growing. Most of us are retired, I would say senior geologists, mining engineers, metallurgists, chemists, physicists, and we have formed this association, and we had 3 major events. Next slide, please. No, sorry, next slide. First is this lithium summit, which we had in T-Hub in Hyderabad, and then we had this so-called first conclave and in February 2025, and on 9th and 10th of October we had early, that means innovations in rare earths and lithium, and many of you have come, they have attended the meeting in Bangalore. We wanted to avoid travel, so both of us came here, and Sandeep and my Dr. Sandeep Hamilton and other colleagues, they managed the show in Bangalore. Next slide, please. Now coming for energy security. This is most important. Now whenever you talk about energy security, we must consider energy trilemma. What is energy trilemma? That means you cannot achieve energy security at all costs. You have to keep in mind environmental protection. So one axis is the energy security, the other axis is the energy, I would say environmental protection. And the third axis is the energy equity. Energy equity means whatever energy you are generating in the country must be equally distributed amongst the citizens. Look at India. If you see the per capita consumption of electricity in the western part of India, in Maharashtra, Gujarat, Rajasthan, and part of the south, Karnataka and Tamil Nadu, are way high compared to the eastern part of the country, Bihar, Jharkhand, West Bengal, and Northeast. So this is not acceptable. It has to be uniformly distributed. So that is called energy equity. The three corners of the triangle on energy security, environmental sustainability, and energy equity. So the World Trilemma Index is given. Trilemma Index is a parameter that tells you how nicely you are balancing these 3 conflicting requirements. And India falls in the bottom 20%, bottom 25% of the countries in the world. I will show the next slide, please. You see the color code, it shows you where your number is, and India, you can see it is deep blue, which is the bottom 25%. The top 25% is mostly the Western countries, North America, and I would say most of Europe. And Scandinavian countries are the highest, Denmark, Sweden, and Finland. They have the very high score of this. Now these are on 3 parameters. As I told you, the largest electric power, India is the 3rd largest producer of electric power and electricity in the world, next only to China and USA. But because of our high population, our per capita consumption of electricity is less than world average, half of this world average. Ours is in the range of 1530, world average is about 3800. And in terms of energy equity also, our score is pretty low. That's why we fall in the bottom. China used to be earlier in the middle 25%, but today, it has come to the first 25% recently, and now it is occupying a position, rank is 12, and the US has gone to 17, and most of the Scandinavian countries, they are within the first top in terms of this. Next one. The other is a Human Development Index. This is a UN parameter that tells you the development level of a country. The development level is directly related to the per capita consumption of electricity. You can see this graph, the graph goes this way, exponential, and this is the knee, and then it more or less plateau. And if you see here, this corresponds to approximately 5,000. So if you can achieve a per capita consumption of electricity in the range of 4 to 5,000 kilowatt hour per year per person, it is more than enough for a country like us. So we should target, right now it is 1500, so we should have a 3 times more higher per capita. And if you have this, then your Human Development Index will increase from 0.6 to 0.8, and Human Development Index are measured in terms of your average, what is your life, whether it is 70 years or 80 years, and in terms of education, and in terms of quality of life, air quality, and all these things. So it is absolutely essential to increase our electricity generation capacity 3 to 4 times from now keeping the environment protection in mind, and and we have to also ensure energy equity, then only we will have a high human development index. Next one. You can see here, you can see the coal. Coal will still continue. If you see the today's statistics, nearly 60% of the electricity all over the world is generated from fossil fuel, whether you like it or not. Take for instance in India, installed fossil power is 50%, installed renewable hydro and nuclear is another 50%. But in terms of generation, we have more than 60% from coal and another 15% from gas. So more than 70% is coming from the fossil fuel electricity, in spite of the installed power being nearly the same. So we will have to increase our contribution in solar and wind, and there is, as you know, solar and wind today, they are the cheapest electricity. But then if I compare what is known as the levelized cost of electricity, that means the total your expenses for setting up a solar or a wind power, maybe the life is about 40 or 50 years, all expenses you put, capital expenses, operation and maintenance, and salary and all these things, and in the entire life of the plant, how much electricity you have generated. So that will give you the levelized cost of electricity. If I take the levelized cost of electricity and compare it, then nuclear compares pretty well. Nuclear power plants are very expensive to make, but the operation and maintenance, many of you are not even aware that the cheapest electricity in India is from the Tarapur Atomic Power Station 1 and 2, 1 rupees per kilowatt hour. Solar and wind are in the range of 2.5 to 3, because as the life of the nuclear power plant, it can go stretch up to 100 years. It is designed for 50, then you have life extension, it goes up to 100 years, then in the 50th year to the 100th year, the nuclear electricity cost is the lowest. So these are all some of the factors we have to keep in mind, and that's why government has very rightly understood this problem and then has enhanced the contribution of nuclear towards our total electricity. Next slide, please. This is the global, from 8,500 gigawatt in this, and we'll have to go another 15,000 gigawatts. So more than double it has to have by the year 2050 to cater to a population. Ever increasing population, it will stabilize in the range of 9 billion people. Next slide. And you can see here the contribution of coal, progressively it will come down as you approach 2050. It is going down, and you can see here natural gas. Of course, in US, coal has been replaced by natural gas, and you can see the wind and solar, they are increasing. This yellow line is this, and you see the blue line, nuclear, and then hydrogen is coming up in a big way. People are talking about green hydrogen, blue hydrogen, and very few are aware of the nuclear hydrogen initiative. Instead of using cheaper electricity from solar and wind power to get green hydrogen at a low cost, or using from methane you can produce blue hydrogen. It is possible to thermally crack water at 700 degrees Celsius by using high temperature gas cooled reactor. The process heat of high temperature gas cooled reactor, the temperature is around 700 degrees centigrade, and by the iodine sulfur process you can crack water and produce hydrogen, and that is the cheapest source of hydrogen production. So hydrogen is going to replace, because it is very benign to the environment in a big way. So these are some of the things. It's good that the coal will be decreasing progressively, but insofar as India is concerned, let me share with you as a professional, our target is by 2070 zero emission programming. How about the aviation turbine fuel? It is 100% fossil fuel, right? So that will continue. And the number of aircrafts are increasing every year. If you can achieve zero by the turn of the century, it's fair. And why not exploit coal to the maximum? But make sure that you have the proper carbon capture, storage, and utilization program. Because whatever CO2 is being emanated from this, you can convert that CO2 into methanol. That technology is available today. So we will have to ensure that the carbon dioxide coming out from the coal-fired station, they are captured or converted into methanol, and that's used as a chemical. Next slide. So these are the environmental protection you can see, and these are the different technologies that are contributing to CO2 and methane emission. And methane, I can see here, it's 25. So most of these things from the CO2, and methane is this portion. And then methane, of course, the lifetime is only 12 years. but CO2 is infinite lifetimes. That's why we have to minimize the CO2 emission. Carbon footprint should be minimized in all human activities, right? Next slide. So this is, you can see the global temperature 1.5, it has already crossed that 1.5. Now they are saying, the UNFCCC, they are saying, we say we'll try to achieve 1.5, but even as long as it is below 2 degrees rise in temperature is good enough. So this year, you know, and because of this thing, you can experience yourself erratic climate change. Hyderabad never can imagine in September, practically every day was a rainy day. Look at the sudden flood in Calcutta. These are unprecedented in Uttarakhand. You name Assam. These kind of climate changes are absolutely dramatic and unheard of. So, and the forest fire. So these are because of the CO2 in the environment. So we will have to make all efforts of containing the CO2 emission, and that's why this is critical. The most important part of the critical minerals of that. You can see here in USA, now their CO2 emission is progressively going down. But we are still a developing country, so our number is going up. China, you can see it is going up dramatically. This is China. Russia is also going up dramatically, and this is China, you can see. So maybe after the year 2000, now what kind of material will withstand 650 to 700 degrees Celsius? These are all high nickel-based alloys, and these are indigenously developed by so-called DST mission. And this consists of IGCAR, Indira Gandhi Center for Atomic Research, Midani, NFC, and BHEL. And collectively, these 4 organizations work together and develop. Next slide, Rita. Next slide. These are, you can see here, 700 to this is the type of temperature for advanced. And here, these are all nickel-based alloys. So, in my opinion, the most important critical mineral is nickel. And nickel and copper, in my opinion, these are the 2 most important minerals which we should focus on. And there is a possibility of, you know, most of the nickel is produced in Indonesia, and then most of the copper comes from the South American countries, Chile. And so we will have to try to exploit the copper from our ores. 5 minutes? Okay. Next slide, please. Now coming, so this is the biggest challenge, the decarbonization in the transportation sector and decarbonization in the electricity generation, and that is the main target of these critical minerals. So you will have to use either hydrogen fuel cell vehicle. This is not so popular in India at the moment, where you use platinum anode, and platinum, as you know, in nature it is 0.005%. Only South Africa, to some extent Russia and Zimbabwe, these are the 3 countries having platinum. But then we will have to have this hydrogen fuel cell where platinum is the anode, and then lithium ion batteries, of course, you can see. And in the electricity generation sector, even you can see in India, as on 31st March 2025, you can see nearly 50-50. I would say 50% is a fossil fuel installed and 50% is a non-carbon based fuel. Next slide. So this is the typical vehicle with hydrogen fuel cell. You can see here, this is the anode, hydrogen is coming, this is the hydrogen battery, and this, it comes here, and then this hydrogen gets ionized and gets proton and electron, and as you know, the movement of the electron generation is electricity, so it will run the wheel here, and then the proton will pass through this membrane tylon and come on the other end and will be released in the form of water, benign. So this is the typical way, and here the most important part is to get the platinum anode. Next slide, please. Now this has a lithium-ion battery, the low price of 1/3, and I think Professor Goodenough was, even at 90 plus years, he was coming to the lab. He is now passed away, unfortunately. So in my opinion, we have to focus on some materials which we have in plenty in India. And let us focus on the sodium ion battery. And instead of, if we can get lithium economically, yes, go ahead. Lithium price is going down dramatically. Why? Because surplus production. Surplus production means less demand. So right now it is going down, but again it will go up. So before that, you take full advantage of the low lithium price now and set up all the lithium ion battery plant and also the energy storage plant, and simultaneously you develop the sodium ion battery. So when the lithium price goes up again, you replace it by the sodium ion battery. That should be the strategy. Next one. So this is the typical sodium and lithium life cycle. As you see here, most of the lithium brines from ABC country, Argentina, Bolivia, Chile, and the spodumene from Australia, directly it is sent to the Chinese, and the Chinese are the custodian for most of the lithium ion batteries. And in India, we are importing the batteries and we are just assembling it. We are not doing anything. We are not making the battery in India at all. Next slide. So these are the applications of, as you can see, most 80% of the application of lithium is in lithium ion battery. But I would like to draw your attention on nuclear fusion. We should not lose track of nuclear fusion. 100 years back, did you imagine nuclear fission? It was not there. Fission was discovered in 1939. And today, nuclear fission at one point of time in the 90s, it was contributing to 16% of the global electricity. I am 100% sure in the next 25-30 years, the fusion will be commercial because a lot of success in the ITER reactor, in the fusion reactor, and there I would say if you see the first wall is made of lithium. And go to the next slide, please. This is a typical ITER reactor, and you can see this wall here, it is all lithium. So in this you have the fusion of hydrogen 2 and hydrogen 3. Hydrogen 3 tritium does not occur in nature, and it produces enormous amount of energy and neutron. These neutrons go and hit the lithium blanket here, and then you get the tritium is formed, and then the tritium is recycled back. And in the process, this blanket gets heated, and that heat you extract in the form of steam, and then you run the turbine. So this kind of reactor, now they're to retain the plasma, they are using about 50 megawatt of energy, but they will be able to generate 500 megawatt from that. So from 50 is the input energy, output energy will be nearly 10 times. And in 2030-35 time frame, this will be, and once it is demonstrated, then the commercial plant will come up in a big way. So we should not lose track of this. And one of the major use of this is lithium in the blanket area of the fusion reactor. So just not on lithium ion battery, we'll have to also keep in mind lithium, and also aluminum lithium alloys is used in the aerospace industry. Next one, please. So I will skip this, go to the next one. Skip this is the hydroelectric power station, and these are thermal power stations. You can see here. The major thrust I've been told to wind up in 5 minutes. I'll do that. And so far as the solar is concerned, now we have in India 300 sunny days. So we should exploit. Today I was taking a morning walk, and I did not find any solar rooftop in this campus. You have a huge campus. So I would earnestly request the professors, please do install your solar rooftop. I was working in Engineering Staff College of India, Hyderabad for some time, and then I said I forced them to introduce solar rooftop, and their electricity bill today is zero. So your electricity bill, you have a huge area. All the parking lots in IITs, in Gandhinagar also, IIT Gandhinagar also, they are all NFC. We have introduced in the solar rooftop in a big way. And now the combined solar wind, hybrid is available. And a big plant is coming up, the Adanis are setting up. But then in the rooftop also, you can see here, you can have the hybrid of the wind and the solar. And this is becoming a reality. And then your electricity bill will become zero. And this is entirely off-grid power. Next one. Wind energy is another. We have 7,500 kilometers of coast. And so far we have not even tapped a single megawatt of the offshore. All our wind energy are in the onshore area. And the fortunate part is wind and solar are in those states where you have plenty of sunshine. Say for instance Gujarat, Rajasthan, Maharashtra, Karnataka, Tamil Nadu. They are both wind and solar. So the hybrid installation will be ideal in these places. Next one. You can see this is Denmark offshore plant. If you visit the city of Copenhagen, you will know the entire electricity of Copenhagen is generated from offshore wind. So wind energy resource can be increase significantly by installation of offshore wind and also increasing the stack height of the windmill. Next one. So these are the different materials that are used for, you can see here, I think I was having a chat with the gentleman from Niti Aayog, and he also shares that nickel and cobalt, these are the two main materials on which, critical materials on which we should put all our money, all our bet, because these are the two basic materials that will be needed for the electric battery, and also for the conventional aerospace industries, and also for strategic material. Next. Quickly, I think skip all this, just to give you a feel of, and then lastly, I would just one word about nuclear reactors. You can see here more than, at the moment today, there are 440 nuclear power reactors in 32 countries in the world, with an installed power of nearly 400 gigawatt. And then this has to be increased by a factor of 2 to 3, and it is expected that it will go so in that way. And the long-term sustainability of nuclear power will depend on the fast breeder reactors. The first of its kind in India is running in fast breeder test reactor for more than, on the 18th we are celebrating the 40th year of APTR, and PAPR, the 500 megawatt reactor, is likely to go critical by the end of this year or early next year. And for the long-term sustainability of nuclear power, we got to have sodium-cooled fast reactors and a closed fuel cycle or the processing. Next slide. Skip. So finally, I think I would skip all these things and come to my concluding statement. The conclusion is that number one priority will be to have a critical minerals map of India. You must know where the location of these critical minerals are. And for that, you should put a lot of money on exploration and also mining. You should identify which method of mining will suit them. Underground mining, or it is going to be an open cast mining. Or is the in-situ leach mining, which is used in the uranium industry for producing 60% of the uranium, can that be extended to some of the critical minerals? And also recovering the critical minerals as a byproduct from the other minerals. So that these are some of the, I think you can skip here. So number one point is that. Number 2 point is that we should have a central agency with hands-on experience. This committee should be a national committee where you should put people with hands-on experience, hands-on geologists, hands-on mining engineers, hands-on metallurgists, who should be able to draw the roadmap for getting or exploiting these critical minerals. And in my opinion, your institute has got a heritage. It's a 100 years old institute with very, very prominent mining engineer, geologist, and metallurgist. So this should be, in my opinion, one of the nodal agencies for coordinating all these activities of exploration and mining and further processing and even recycling and recovery of these nuclear materials. I'm sorry I had to cut it very short, but anyway, that's life. Thank you very much. Answer. Please feel free. अरे स्टूडेंट्स क्या है भाई, पूछो तो कुछ. It is better to be fool once than to remain fool forever. So if you have any query, please ask. Don't feel shy. You see, thorium was in prominence when a lot of uranium was not discovered in the 70s and 80s. But in the 80s, major discovery of uranium took place, in Canada particularly, in the Athabasca Basin in Canada, and in Australia, and in the South African countries, right? So that's why thorium for the long term, it will be definitely used. After the uranium is used up, then the thorium. So tens and thousands of years, as I was telling you, you can consider the nuclear energy as something like a renewable energy if you make potential use of all the natural uranium followed by utilization of thorium resources. But thorium ores are always associated with rare earths. As you know, monazite is nothing but uranium, thorium, rare earth, phosphate. So you are having three components. You are having the phosphate, which is again a critical minerals, because if you are making this lithium-ion batteries, phosphate is a very important component. And then you will hear about, I think, a lot of things from, I think, from IRL, who's come? You are the guru. You should. I have come here to listen from you guys. So he will share his thoughts about how to recover neodymium. To the best of my knowledge, you know, we have accumulated a lot of rare earth chlorides, and they have to be exploited. We are having predominantly light rare earths. Mainly, I would say neodymium and हमारे पास praseodymium है, and dysprosium is very small amount, because along with the monazite ore we also have xenotime in our ore. So, but we don't have the basnisite, which is the major ore for the rare. With the Chinese and the very limited, but mostly ours is this. So they will share their ideas on how to exploit the rare earth, converting the rare earth chlorides into oxide, and then subsequently making the metals by hydrofluorination, followed by calcio or macroscopic reduction. And then how do you make the components? Usme to aur bada challenge hai. That Ranjan ji will tell us how you make the components of this. And after you make this, after you 2.5 years, 3 years, magnet ka life hota hai. Chota. Bada windmill ka 25 saal tak jata hai. How do you recover the rare earth and then recycle them back in the system? That is the biggest challenge. So thorium indirectly, in that respect, if you can make full use of the other minerals that are associated with. Abhi kya hota, we always fall for good, and pardon me from IRL for saying, हमारे time I was also in the IRL board. उधर को target होता है, आपका इतना revenue देने का है, उसमें इतना देने का है DAE को. So they were trying to earn quick money by selling the ilmenite and rutile, because rutile and ilmenite, there is a huge demand. Because हमारे बीच में ilmenite, rutile, garnet, selenite, zircon and monazite. So ilmenite and rutile was the main bread earner for IRL. Abhi dhyan zyada gaya on the rare earth, and once we develop that technology, it should be possible to earn a lot of revenues by sending them. And here, please go for cooperation and collaboration, because it is stupidity to waste your valuable time by rediscovering the wheel. No, you jiske paas hai technology, if is prepared to give, join hands and get that and scale it up. Any other queries, please? Yes, please. Yes, sir.
Good morning, sir. It was a nice presentation. I am Sahendra Singh from Department of Applied Geology here, ISM Dhanbad, and I am an economic geologist. We teach economic geology about the ore deposits. On behalf of students, I just want to ask a very foolish question, if not as a professor, but I think it's pertinent. That actually we are always talking about critical metals and non-metals. So why we are calling critical minerals? But everywhere we are talking about critical minerals.
You are absolutely right. I fully share with you. In my opinion, had they called critical elements, I would have really appreciated. Actually, it is critical elements. What they meant was the minerals that are associated with the critical elements. That's what they meant. So, ठीक है, terminology के लिए सुनने में अच्छा लगता.
But sir, in that case, all the minerals nowadays, it's not only, if suppose we call monazite is a very important mineral, it's a critical mineral.
Suppose of course it's a critical mineral.
Suppose we call.
Of course.
That, you see all sulfides, all pyrite, chalcopyrites, phyllerites, hematite, they all have the trace elements,
absolutely.
Cobalt, nickel and all.
Yeah, you recover it. It's critical minerals.
So,
you are absolutely right. I am with you 100% on this. What they meant was, all minerals in which these critical elements, which are used in energy generation, environmental protection and national security, they are exploiting those minerals. That's what they do.
thank you, sir. Thank you.
But then they have to put the economic factor, because in any mineral, you have to mention, just finding out the mineral deposit is not good enough. What is the cost of extraction? In uranium, we always say the uranium deposit is so many million tons at a cost of say $130 or less than $260 per kg of uranium. So the extraction cost should also be given in the critical, not just the deposits. Also the deposit at what cost, that should be given. That's what I'm saying. To establish the critical minerals map of India is the most important target, and I think this institution should take the leadership in that area.
Thank you.
Someone, yeah, please.
Hi, good morning.
Yeah.
Sir, in one slide you mentioned like about nuclear reactors. Four are, I think, suspended, like you mentioned in the sir. Why 4 nuclear reactors are suspended and not operated?
No, they suspended for long maintenance. You know, sometimes even the pressurized heavy water reactor, if you take, after 12 or 15 years, you have to do the retubing. So that retubing takes about 1.5 years, 2 years. So that is temporarily shut down for retubing, and once it is retubed, it will start again. Yes?
Sir, we can discuss over tea time.
Thank you so much, sir, for such an encapsulating talk. So I'm pretty sure all of us will try our best to grasp what the wisdom you have shared. So, and it's also, I would like to say that it's thrilling for us to meet a person who was born before our country attained independence. And I can't wait to hear the experience.
Now we request Dr. Sandeep Ghosh Chaudhary, Director CIR NML Jamshedpur, to decorate the Chief of Guest of Honor with a shawl and present him a memento.
Thank you so much. Thank you so much, sir.
We now commence the session 1 of second day, focused on critical mineral resource development, challenges and opportunities. This session will highlight India's progress and prospect in critical mineral exploration and utilization.
We welcome our session chair, Shri R. Saranabhavan. Shri R. Saranabhavan is a deputy advisor in NITI Aayog since 2012. He took up the role after 17 years in the Ministry of Mines and Indian Bureau of Mines, having been inducted by the UPSC. He holds a master's degree in applied geology from the University of Madras. Yes, sir. And sir is the deputy advisor of NITI Aayog. We are truly pleasure to have him with us today.
Joining him as the co-chair is Professor Nikam Suresh. Professor Nikam Suresh has held a position as Emeritus Professor and Professor HAG at the Department of Fuel, Minerals and Metallurgical Engineering at IIT Dhanbad, specializing in the areas of coal mineral and beneficiation. For his significant contribution, he was honored with the National Award by the Ministry of Coal and Mines in 2000 and Coal Beneficiation Award in 2000. In collaboration with Wales Mineral, he co-designed an industrial involute cyclone separator for which a joint international patent was filed. Professor Suresh has published 77 papers in revered international journals and has guided 18 PhD students.
We kindly request Dr. D.K. Singh to board the dais in order to felicitate our chair and co-chair. Please give them, invite sir with a round of applause.
Yeah.
We request our session chairs to kindly take their seats and please begin the proceedings.
A warm good morning to all. So we are beginning this second day session. I think we are running short of time now itself. We are late by 1 hour. So we are requesting the speakers to strictly adhere to the time limit of 10 minutes. So we have the first speaker. First speaker is Shri Mohan Babu Verma, former director AMD. Mr. Verma is a gold medalist in applied geology from Aligarh Muslim University and a veteran of the Department of Atomic Energy. He is renowned for his work on uranium, rare earths and critical minerals. Currently he is a consultant in NSES. Now the floor is yours, sir. Please stick on to the time limit of 10 minutes. And after the end of the session, we'll take the questions. We don't want to have questions in between because that will kill the time. That's why. Fine, sir. Thank you.
Very good morning. I'm very sure that after listening Dr. C. Ganguly sir, you are all thrilled. I'm thankful to Dr. Singh, Dr. Anita Kumar and I think other organizers for inviting me. This Indian School of Mines, I have come back after maybe about 42 years. I came somewhere in 1983 when your Executive Development Center was started. I was one of the trainees for geostatics course from AMD. Now, ISM Dhanbad has been given an opportunity, rather selected for National Critical Mineral Mission Center of Excellence. Hope that this renowned center will do justice. Yesterday also I was going through a very important news that in UK India Critical Mineral Supply Chain Observatory, this center is also chosen as one of the satellite center along with Bombay, GMDC. So hope lot of onus lies with them. My talk is basically for supply chain resilience of critical minerals, Indian perspectives. How this movie is okay. Yeah. What you see is basically, I think it's not working. So, basically, India is the fastest growing economy and soon to be nation, $5 trillion. Lot of dependency. I think Dr. Ganguly has covered most of that part. Some of the important critical minerals we do not have any deposit. Rather, we have to go for secondary resources or from some of the recycling, those type of the domain, it will. Energy transition, supply chain is a basic geopolitical risk, and also Dr. Ganguly has told very clearly about the national security. That part is very important. I think I will come down. That will be better. Achha. What do you see recently? This gallium and germanium wafer supply. India imports around 95% of its annual requirement of the chips. Something around hefty bill of 1.7 lakh crores. Chips require plenty of applications in different things. We have got a lot of germanium and gallium resources in the country, particularly from the bauxite ores, even from the coal deposit germanium is available. Why we never made any effort to recover these resources? Unless until basic material is available to your doorstep, any technology can grow. That is what the challenges are required. Recently, Government of India launched semiconductor mission with a pledge to invest about 76,000 crores. Do you think the supply chain of critical minerals is a global crisis? If you will see those kind of things, the reason behind that, if some countries which own all these materials, if they restrict your supply chain, there will be a crisis will come. And those crises, you see number of newspapers, those reportings are there, where first China blocked for gallium germanium, later on they blocked for strontium, this antimony, subsequently they blocked for heavy rare earth supply, some 7 rare earths, then they blocked for magnet. And that is how suddenly there was a big paucity, big problem in the country. I have a lot of overlay in the slides. Okay, this position is correct. So, supply chain resilience of critical minerals become vital globally and India too. Why lack of attention on mineral sector? No new mineral deposits in last 20 years. Lack of building, processing technology and facilities. Lack of focus to develop complete value chain. The minerals which we have got available, we have never attempted to develop the complete value chain. What is required, what is essential for the industry, what is required for today's use, we thought. We never have that type of the foresight. Maybe having, but maybe confined to certain sectors. Now, green energy revolution has given some kind of the ray of light. Flourishing Indian economy is also one of the factors. The focus has come. And altogether with a lot of motivation from our beloved PM, manufacturing sector also getting lot of attention. And most important is lack of international collaboration and diversification of the supply chain. We never thought of diversification. And if you will see, the net result comes why some of the events, so sorry sir, let me come back. Lessons we learned from COVID-19. No doubt, this thing has given lot of lessons to a country like India. Ukraine-Russia conflict. Israel-Hamas conflict. Chinese ban on supply chain of critical mineral commodities. Lessons from Operation Sindoor. Focus has come directly on indigenous manufacturing sectors. Digital economy, Atmanirbhar Bharat. These are our certain things. What you have seen that a lot of push has been taking place in this sector. Some people develop rare earth sector very well. Till 90, only one single country, US, where mountain pass was the sole resource of supplying of the rare earth. Later on, because of the environment and other issues, entire focus shifted to China. Within the 20 years, China has built up and it has emerged as one of the largest suppliers globally. Rest of the nations, because it is lot of environmental pollution, effluent generated in the water, so many hazards. People did not develop those facilities because the material is easily available. By single event of 2010, when there was some conflict with the Japan, people started getting signals that minerals can also become something like a diplomatic tool to mend the things in their favor. Many of the industries, China asked them to shift to the Chinese, Japanese industries particularly, if they want rare supply. And all these geopolitical strategies led to people think of those, and these are all restrictions which have come into the place. So, when China put a ban on supplying these rare metals, immediately they wanted some kind of the export licenses, some conditions put forward. 30 companies immediately applied for Government of India. Government of India gave the clearances, and in May itself, Chinese, they rejected all these things. No, you cannot go for any kind of defense, and user certificate is required, and lot of paperwork and all these things. Therefore, Chinese dominance in exploration, mining, processing, acquisition of the resources has emerged as one of the major problem for the country. Our problem is 80% RE, we are dependent. We have got the rare earth associated with the placer deposit, something around 7 million tons. Then we have got rare earth deposits associated with the hard rocks. 1.1 million ton is Dhanbad deposit. Close to another 4 lakh tons may be there in Sivana Ring complex. And of late, those deposits started working somewhere around 2015, not before that. Had we worked from 2000, probably another few more million tons deposit would have been added in our kitty. So what, sir, you were telling about the focus on exploration and all these things? It all goes with the kind of requirements. Only thing, sometimes we wake up little early, sometimes we wake up very late. And we wake up a little late, then we have to face the challenges of supply chain. I am giving you one very small glance, 44 million tons. Wherever gold deposits are there, everything is in the kitty of China. You will be surprised to know ABC countries control lithium, particularly Australia has got hard rock deposits, but almost 70% refining of lithium takes place in China. So wherever the material is mined, it will go to China for processing. Once we go to the China, control will be there in the hand. DRC, Democratic Republic of Congo, 80% cobalt mining is confined to Vietnam. Most of these things, nickel, dominated by Indonesia. Therefore, you try any level, anything, unless until you develop your indigenous resources, probably you may not able to come these kind of things. And Chinese have invested large amount of money in overseas acquisitions. So this is their long-term strategy. If we will take up all these things little faster, we can able to do it, better supply chain maintenance. Otherwise, it will be difficult for us. And I will be just, my time is very short. So. This is again focus. You see, particularly that most of the things, including the graphite, the processing takes place maximum in China. Why other countries do not develop? Question comes. There is no dearth of technology, there is no dearth of intellectual, there is no dearth of laboratories. Only thing, focus lies somewhere else. Unless until we focus on these type of the resources, their development. You see the battery cells, it's a very difficult that most of the things lies total control of the China. Nobody has got any kind of the control. Major concern now, if you want to ignore China, you have to diversify. Now the question is, who is the substitute? Better substitute of the China. Even you want to make somebody emerge as a substitute of the China, you require at least a decade maybe 4 to 5 years minimum, and by the time the process set up, production comes, quality controls and dates are matched, that will take nearly a decade. And that is what the people say, even whatever the efforts are made by US, probably in next 10 years at least it will take to be, things will get strengthened. This is the position of our country as on today. We don't have any single deposit of these things. Therefore, we have to focus. These are few policies decisions which have been taken. I need not to repeat all these things. Policies and directives to promote upstream sector, very nice. India is also giving mandate for hard rock mining to JMDC. Hope that maybe in 2 to 3 years, some kind of the at least upstream production will start. IIDL is also doing some kind of the. Where? What is happening? I am not welcome. Come to my last slide. Huh? I think we should operate from that. That will be better rather than. Just come slide number 15. I will finish within 5 minutes. 15, 1 5 will come. Next. These are the all efforts have been being made somehow or other to have supply chain in the country. Next. Next. Yeah. Now, there are number of good deposits in the country where it is possible that our R&D centers should focus on those deposits. They can able to extract good resources, even they can able to do the process development. Cost factor should not be the prime consideration. In my opinion, cost factor should come subsequently. First you try to focus on recovery. How much percentage of the recovery you can get, and recovery should be compatible with ESG parameters, environmental and societal parameters, though it should go along with that. Third thing is, once you touch a deposit, try to recover maximum content of the mineral content from the mine. Because once you touch the deposit, it will not be used second time or third time. You cannot go back. What is happening is the Kolar gold field, which was closed long time back, when they were mining at 7 ppm of the gold, today even 2 ppm is economically exploitable, but it is very difficult to go back there. Number of other potential resources, including tungsten and osmium, is there, which has never been recovered from those things. So the deposit is available, resources are available, but can be able to do today. There are a lot of challenges associated with that. I don't want to go into that complexity further, but we have deposits in spite of having the deposits. Next please. These are the basic practices which was followed: stockpiling, recycling, promote alternate technology, investment in non-Chinese strategic deposits, and reduce dependence from 90 to 60%. This is the model followed by Japanese. We will surprised to know many of the critical minerals are not at all available in Japan, but they are sustaining very well. Very well they are sustaining. There are number of organizations, they have JOGMEC and other things, they have made higher investment, they have assured their supply chain for their industry, and their industry is never been in crisis. So next. I am presenting, for example, they have done 3.8 billion investment in critical minerals, investment of urban mining, developing new technology sharing platforms, and risk sharing mechanism. That is what Indian industry should come forward. Without risk sharing, probably it will not be possible. Next. In case study 1, this is how.
Sir, can you conclude in another 1 minute?
1 minute, okay. This is what Japan, okay, Nick, please finish. Going to the last slide. Just stop, okay. So, in my opinion, we should not restrict only to one country or one nation supply, rather diversify your supply chain. I think you are sitting there, Sarvamon. You can carry this message very good. So far, we have not given much focus on the startup in the mineral sectors. When the young generation are coming, they have a very good ideas, number of processing there in their mind. They may think out of the box, may not able to follow a straight path. There may be some steps they can able to overcome. Therefore, the startup in the mineral sector should also be promoted. Let us experiment. There is nothing wrong to doing some kind of the experimentation. Development of integrated value chains, mines, metal and the law. We should not confine only mining. Mining is our focus or exploration is our focus. After mining, once you get the ore concentrate, you get the metal oxide concentrate, we don't have any supply. So many people tell very clearly, we don't have any supply, we don't have any buyer, we don't have any alloy, no industry will come unless until. So please focus mines, metal and alloy, that's the complete supply chain. Many people have spoken about fly ash and all these things. Overseas acquisitions, definitely, but with a rider that you should not land up in a property or in the assets which is not having a long-term sustainability. We choose those things which are really having a proper assets based on the sample borrowed data, which should be assessed by some of the experts and where potential exists. Otherwise, again, you can land up in a problem. Focus on Africa, Central Asia and Latin American countries. That is probably still large scope is there, although China has got their footprints there, but still some scope is there for India. Then R&D for alternate to HRRs. Why we should be dependent only on HRRE or rare earths or lithium? As Dr. Rambo was telling, lithium ion battery, why not to shift over to some other nickel ion or some other kind of the alternates? A strategic autonomy focus on the domestic capacity building. We should also focus, in spite of the costly resources are there. Case is cited by Dr. Ganguly in the morning that we have got 80,000 tons of uranium deposits. Now more than 4,25,000 tons. Our low-grade ores, probably this type of the ore may be lying in the tailing pond of some of the rich countries, but nothing wrong in that. Japan uses 22% of FeO content, 40% of iron ore content we are putting on the roads just in the form of boron on the laterites. So it is the resource which you have got. If you have indigenous supply, our reactors are running and a lot of fuels fabrication is being done. Similarly, SPV in the mineral sector. That's all. Thank you, sir.
Thank you, sir. Adhering to the time limit. A big round of applause to Dr. L.B. Verma for presenting a comprehensive role of critical minerals in the geopolitical spectrum. I think with the support of NSC, yes, we can reach the goals ahead, sir. Thank you, sir. Thanks for the wonderful lecture.
Next speaker is Dr. Kacham Anand Rao. His biodata is very long, but I cut shorten it because of the short of time. He is basically a chemical engineer and a computer science graduate and did PhD. Now currently he is holding the position of CMD of UCI. I invite Dr. K. Anand Rao to deliver his talk. I think we are restricting the presentation time to 10 minutes. We understand it's very short, but it's a demand of the time that what we have to stick to it.
Good morning. Good morning. Actually, I prepared 30 minutes lecture with the idea of requesting 10 minutes more time. Anyway, I try to rush through the slides. First of all, I thank the organizers and Dr. D.K. Singh for inviting me to give this presentation here on the current status and trends in exploitation of few critical metal ore deposits occurring in India. So I visited ISM Dhanbad around 30 years ago to undergo an executive development program. And I was looking at the buildings to recall my memories. Then I was looking at the people whom I can recall. Then I was very happy to meet Dr. Professor Nikam Suresh, who taught me in that program, executive development program. So very nice, sir. I could recall all my memories visiting ISM Dhanbad. Not only the buildings, but with people, interactions I had with people. So coming quickly to the topic, the critical metals, as you all know, they have no substitutes. They are economy drivers, and they are crucial to technology, but their supply is at risk. So they are essential for substances, but availability is at stake. As you can see, the definition depends on who is asking, where and when you ask. Like arsenic is critical only in the United States, and some are iron, silver, they are never critical, and yellow colored ones, they are critical elsewhere, but not in United States. All the blue colored ones, rare earths, etc., they are critical both in United States and elsewhere. So my present topic will include the extraction technology developments with regard to rare earths, lithium, which have been moved from atomic minerals to critical metal by state government of India, and uranium, of course, as Ganguly sir was telling, it is an atomic mineral still, but it is also a strategic, critical mineral, taking the role it takes in energy security. These are the main challenges. We have there are lean tenor ores, which leads to high throughputs, safe disposal of large volumes of waste, similarly fine dissemination, presence of clay. All these are the challenges, and complex mineralogy, multi-metallic ore, these lead to different challenges. The carbonate ores, refractory minerals, so they all pose problems which require alkaline leaching, drastic leaching. Alkaline leaching is mild compared to acid leaching, so they require drastic conditions, and we require advanced modeling control systems, etc., to overcome these challenges. So for this we have technologies like advanced mining and characterization technologies like geometallurgy. The conventional metallurgy relies on the called average grade, which rarely exists in reality. So if you have a link between a metallurgist and a mining person, then there will be a feedback loop, and that type of strategy is coming up. This geometallurgical approach, which will increase the resource to reserve conversion factor from 50 to 70%. This is what studies shows. Then PEMSCAN, advanced characterization techniques, and then energy efficient process like high pressure grinding rods. The ore pre-concentration techniques, Nelson, Falcon concentrators, bio-heat leaching. Also the process intensification techniques like electro, microwave, assisted leaching, automation, and then the emerging technologies like salvometallurgy, where you replace inorganic solvent with organic solvent. In deep eutectic solvent, supercritical fluid extraction, this can be applied for even uranium extraction from the ore. It has been tried by IGCAR to take uranium from the tissue paper waste, active tissue paper waste. So this can be generalized or extrapolated to extraction of uranium from ore sealer. So these all are characterized by energy efficiency, eco-friendly nature, high process efficiency, water economy, and minimum effluents, and which are economical. So I will just focus on these case studies of rare earths, uranium and lithium with the key drivers as mentioned in the previous slide. So the just small introduction about the rare earths. If you see the substitute performance table, the rare earths cannot be substituted by other elements, and rare is a misnomer here. Their economic concentration is rare, and economic concentration does not depend on tonnage or grade, but they are dictated by complex mineralogy, how it is extracted, how they are extracted. And you can see only 5 out of 7 critical rare earths, that is NdPr, terbium, dysprosium and polonium. These form 90% of the global RE market. It's not moving. So I would see, as you all know, applications of rare earths are very crucial for energy, clean energy systems. The production of rare earths, as you can see, when China imposed ban on their exports, then the other countries started increasing their production. China's contribution came down, but nevertheless, more than 90% of RE still is controlled by China. See, the market is very volatile and highly uncertain and filled with opacity. You can see various countries producing rare earths. So, but there is a physical beneficiation step in all the processing. No country is processing less than 30% rare earth grade. So, whether you take China, India, we have to beneficiate and then go into chemical extraction, because extraction of rare earths involves very drastic conditions. The rare earth minerals are very refractory. So, here we adopt the acid route is cheaper but environmentally unfriendly. Alkaline route is costlier but eco-friendly. USA and India, we are adopting alkaline route, whereas other countries are adopting acid route, which is environmentally very unfriendly. So what is presently IREL is producing rare earth with so much reserves available, but there are certain problem. There is a radioactivity involved in monazite, so we can look for non-radioactive resources for rare earth production. And so the solution could be order. You can concentrate on order deposits like Ambadongar, Sivana Ring Complex, and coal fly ash. Which see, this work was done when I was in BARC. So a lot of exhaustive studies were carried out how to extract rare earths from Ambadongar ore. So many samples were studied. The RE grade varies from 0.3 to 3% REO, and magnetic feed REOs are 10 to 12%. The characterization has shown that the rare earths are very finely disseminated and also coated with iron, which will not allow you to take up any physical beneficiation processes. So direct chemical process was inevitable. So after all this was a flow sheet evolved. Here I will not go in details because short paucity of time. After this salvation, grand leaching, then sulfation roasting, we can get products, not only rare earth product, magnesium as byproduct, and also niobium is available. So we should look at to develop comprehensive extraction flow sheets rather than looking for only rare earths. So you can look for other byproducts, valuable byproducts available in the deposit. So next is Batikera, that is in the Sivana Ring Complex. This has valuable other byproducts like zirconium and niobium also. So if you look at here again, the physical beneficiation was not feasible. The characterization studies showed that the multi-minerals of rare earths are present in this, and heavier rare earths are associated with zirconium. So the detailed studies, these are the detailed studies. I will not go into details. The final the agitation leaching did not work, it gave only 60% recovery, whereas pure leaching has yielded more than 80%. Again, we sought for a mild conditions of leaching conditions. Then once it comes into aqueous phase, so the direct precipitation was not feasible because of high sulfate concentration. So exhaustive studies were carried out to do niobium zirconium recovery by solvent extraction, and where the solvent alicate with isodecanol as a modifier, the ratio was very important. After so many experiments of extraction and the stripping, this was evolved. There is certain ratio between which this has to be maintained. Then the raffinate, from the raffinate one can recover rare earths as rare earth fluoride. So fly ash, again we did lot of work on this. So this, these were the samples taken up. From Neyveli lignite we found 2000 ppm of rare earths, and this was a flow sheet developed. It is again followed by leaching under mild conditions, followed by solvent extraction for HRE and LRE separately, and the simpler alternate flow sheet has been developed at Mineral Processing Division BARC, that my colleague Dr. Ramkaran will explain to you in the upcoming one of the presentations. So now coming to uranium. Can you move back? Two, three slides. Uranium. Just one slide. Yes. So the more than 50% of uranium is extracted through in situ leaching. It involves basically acid or alkaline leaching routes. Next slide, please. The Tumalapalli was a milestone achievement for Mineral Processing Division of BARC. We had a lot of challenges, like it is finely disseminated. Uranium is present in finely disseminated form, uranium titanium complex, etc. And there is a problem with the sodium sulfate production. So all these were addressed. And next slide, please. Yeah. So lot of combinations were tried, like physical beneficiation, etc. And once upon a time, this was declared as not techno-economically not feasible process. But later on, there was a breakthrough. Next slide. So we went for alkaline leaching, which was a major breakthrough, and we did pilot plant studies. Then exploratory mine sample, on the exploratory mine sample in the year 2012, the Tumalapalli plant was commercial mill was commissioned. Next slide. So this is a complex flow sheet. Again, there is a lot of recycles. I will not go into details. And this is the first uranium plant established in the country. And then there is another uranium deposit at Kanchankai. We have gone to, because of high sulfide concentration higher than Tumalapalli, so we could go for hybrid flow sheet. Previous slide. So one stream will go for acid leaching, another stream for alkaline leaching. This was again a hybrid process flow sheet developed, and finally we could produce uranium concentrate at laboratory scale. Next slide, please. So Rajasthan, this is the upcoming uranium mill in the country. So for 12 million tons were proved reserves proved by AMD, and the underground mining 2,500 tons per day is planned. It is a acid leaching like Jadavura type of ore. The status is we expect it to the commencement of the commercial mill is expected in 2027, and expected commissioning of the mill will be 2031. So this is actively being considered by UCL. Next. Lithium, as ABC countries are controlling 40% of the lithium production and 60% is spodumene from Australia. Next slide. So next slide. So this is a flow sheet developed for extracting lithium from spodumene mineral, 66% pure. and these steps are mainly the degradation followed by sulfation roasting, and all the parametric optimization studies. Exhaustive number of studies were carried out at laboratory scale and bench scale, and this was demonstrated at 100 kg scale. The final product was lithium hydroxide. So this is the last one, that is the process for lithium extraction from lipidolite ore, 40% pure. Again, here also lot of work has been carried out in mineral processing division laboratory of BIRC. So these are the various steps. Parametric optimization were done at each stage. So that finally we could get lithium hydroxide of 99% purity. Again, this will be explained in one of the future upcoming presentations today by my colleague Dr. Reshu Sinha. So I won't go in details, and there are byproducts from this. The rubidium, cesium, sodium sulfate and potassium sulfate from this process. So next slide. Yeah. Thank you. I tried to rush through the slides. Anything we can discuss over tea time. Any clarifications?
Questions you can take later. And I thank Dr. Anand Rao for making such a nice presentation. And also remember me of 1996, which I myself had forgotten. Thank you, Dr. Rao.
So our next speaker, strategy and business development, corporate planning, projects, technical services and marketing. The floor is yours, sir.
Good morning to all, and thank you ISM Dhanbad for giving me this opportunity to present here along with the organizers of the quest. Today my topic is rare earths, a catalytic material for advanced technologies. So sir, before you say, I will stick to 8 minutes, I think. So this is the summary of my presentation. It will be the introduction, global scenario, the Indian context which people out here are not very clear about. Then our expansion plans and valuation efforts, the future and the conclusion which we have. So first the introduction and global scenario. This is just a brief introduction on the rare earth. Everybody knows about that. But from the Indian resource, what we produce is, what we have is rather lanthanum, cerium, NdPr, samarium, gadolinium and dysprosium. And these are the properties of the rare earths for which they are used as a niche material. They are magnetic, catalytic, optical, nuclear, luminescent, electrical, metallurgical, to name a few. So they find a huge range of applications across various technologies. The occurrences, the primary ores are carbonatite and alkaline igneous rocks, which you find the drawing below. And the secondary mineral ores which are present in India are the ionic clay and tracer deposits. And these are the global rare earth resources. India now ranks among the third, with China being the first, Brazil being the second. Vietnam has been downgraded of late from 21 million tons to 3.5 million tons. But the Indian resource is locked with radioactivity, that doesn't come out anywhere. Now coming to the global RE ore output, we can see in 2024 it was only 390,000 tons total output. So ideal production is not captured here because our details are not available in the public domain. Now coming to the global RE demand, you can get a snapshot view here. Main goes to the permanent magnet, catalytic materials and all. And if we go to the RE demand by the countries, China has 76% of the demand, Japan 4%, US 9%, Europe 6%, others are 5%. So where is the Indian RE demand? There is no percentage out here. That is because there is a total lack of midstream industries in the country using rare earths. There are false narratives being created by the industry house, citing shortage of raw material, but the main objective is to enter the upstream part of the activities where the capabilities do exist. So that is a false narrative which has to be countered. Now coming to the quantum of RE usage, we use it in minuscule quantities. For example, in polishing powder, cerium lanthanum is used in glass polishing powder, but it is 0.2 gram polishing powder powder consumption per square foot only, and their cerium and lanthanum is 62 and 17% of that 0.2%. Then coming to FCC catalyst, 1.16 kg FCC per ton of crude is used, and out of that 0.9% is lanthanum. Similarly, the biggest consumer is magnets. In EVs it is 2 to 5 kg of RE magnets per car, out of which rare earths is around 27, and in windmills it is around 500 kg magnet per megawatt. So we should not be considered as bulk minerals because the usage is in minuscule quantities. Now this is a composition of REs in magnets. Basically it is NdPr is around 27 to 30% maximum, and as and when the operating temperature goes up, the use of dysprosium and terbium also goes up, which can be seen from this slide. And this has been taken in with discussion from experts across the globe. And now Verma sir was talking about the restrictions on RE. It's all started in 2010, and in 2015 China centralized the RE companies to 6, and in 21 to 4, and in 23 they started putting restriction on RE extraction and separation technologies. In 24 again reduced the total number of RE companies to 2. And what has been happening from April 24 and again in October 25 is all evident here. Now semiconductors and dual use technologies are in the air. And what the countries have done for supply chain security. US has taken 3 steps with MP Minerals. They have invested in equity, provided 10-year floor price of $110 per kg of NdPr products stockpile, and ensuring 100% magnets produced at MP's new facility that will be purchased. Similarly, France and Japan have signed an agreement between Carister and Iwatani. Australia as well as India. In India we have NCMM, then we have the National Critical Materials Policy and the initiative taken by the Ministry of Mines in changing the MMBR Act. Now coming to the Indian context, so this is the biggest challenge for us. China, which is the largest producer, they mine the rare earths from a ore containing 6% REO, but in India it is 0.06%. US was doing mountain pass earlier, but because of environmental issues they stopped it, but now they have restarted it. That has 8.24% REO. So our grade is very lean. That is why the number of stages of processing is quite high. While they do it in 3 stages, we do it in around 5 to 6 stages, and that way it is associated with radioactivity. This is the overview of IREL. This is our mining practices, where we collect raw sand from the beach washings, carry out dry minings internally, and also mechanized mining. So this is the first stage of our operation, where we increase the heavy mineral grade from where we get the monazite from 10% to 88%, and thereby the REO content from the ore we get around 0.06%. And then in the second stage, which is concentration, we increase the HM grade from 88 to 95%, and the REO grade increases from 0.06 to 0.6. And this is the mineral processing stage, which is the third stage, where we get the rare earth bearing mineral at 25% REO level, and in turn 6 other minerals get liberated from radioactivity. And this is the fourth stage where we do the RE beam cracking and get mixed RE concentrate and tri-sodium phosphate along with strategic compounds. Here the REO value is around 45%. That is the fourth stage. And this is a flow sheet of cracking of REBM in detail. the final stage is RE refining, where we get 99.9% purity of NdPr, samarium, cerium, lanthanum, dysprosium and gadolinium. Then the value chain, people are aware of the radar permanent magnet plant which we have set up in Vizag. So we have started supplying to DRC and DMRL. It has been tested and cleared. All have also passed the real-time testing and received, and Ideal has received the first order for continuous supply. Then ADA, we have supplied the magnets and it is under testing. Similarly, we have received some inquiries from other institutes guided by DMRL and we are working on that. The second initiative is the rare earth and titanium theme park in Bhopal, where we have established technology to produce lanthanum metal. We are into discussions with R&D labs for addition of lanthanum and cerium to improve the properties of various steels, including those for strategic applications. Similarly, we have set up a facility for cerium metal, and all are zero discharge technologies. Then we have RE recovery, that is recovery of rare earth from end-of-life magnets. The yield is around 92% and purity we are achieving is 99%, and all these technologies have been established with the support of BRC. And recently we have set up an ND metal technology, and we are in the process of supplying some quantity of ND metal to DMRL to find its suitability for the production of ND-FeB magnets. So this is the global RE ecosystem and the contribution of IDL, where we are in the first 4 stages. The 5th stage we are not there, but we are in mining, extraction and refining, production of metals as well as magnets. In the future plan, so there are around 4 new leases which we have applied to expand our capacity, which I will be telling shortly. So our present capacity in mining is 10 million tons. We will be increasing 5 times. Similarly, for mineral processing, we have 1 million ton. We will be increasing it to 3 million tons. As regards rare earths, it is 11,200 tons, which will go up to 33,000 tons. And REO tons will produce around 13,000 tons of REO, which will be producing around 2,500 tons of NdPr, which will suffice 8,000 tons of E. And the next feature which is under evaluation, critical minerals and rare earths. Various R&D labs are working on mine overburden, mine tailings, metal slag, fly ash, red mud. Once the feasibility is established, we'll go ahead with that. But the challenges in that is the low content, requirement of skill development, high energy use, multiple stages, mineral losses, and hazardous waste. So that has to be taken care of. And in conclusion, is green energy truly green? So this is left for deliberation, because 1 megawatt wind turbine contains copper, magnets, concrete and steel, and these materials are often mined in ecologically fragile conditions. So these kind of things we have to take into consideration before declaring, is the green energy truly green? So the constraints in case of IDL is radioactive materials which are heavily regulated, and they are difficult to handle and dispose, long gestation period of mining, large number of stages to reach the end product, and different characteristics of different ores. So the way ahead is considerable environment cost of energy. There is a need to switch to sustainable sources, balancing the demand for RE with environment considerations. Governance, mining, processing and recycling. We have to put a thrust on that. Intensify our efforts on recycling and dedicated R&D in mission mode. Not only process, but plant and equipment, material of construction, zero waste, and also to include scaling. Thank you.
Thank you, sir. Thank you for the presentation. Actually, one thing which is clear from this presentation is actually India has declared 24 critical minerals. In that, only 1 critical mineral we are well off is REs. For that, I really compliment IRL and especially Dr. D. Singh, who was pioneering this critical mineral chain, especially for RE sector. Thanks for the presentation, sir.
Thank you.
Now I think
I request the three speakers to come onto the dais because we have to facilitate them because one of the person has to leave. And I request Dr. D. Singh, former CMD IIL, to do the facilitation. We will break for tea 10 minutes and then we will assemble.
का रेंज इतना ज़्यादा कहीं हो जाता है ना, और दूसरा वही हो जाता है। इसका या जो है इतना ज़्यादा डाउन हो रहा है ना, फोकस में है लाइट फोकस नहीं हो रहा है, फोकस में है ना
कहाँ से सब डीआई के लोग हैं क्या बताना है बरबट्टा क्या
नाम लाइट भी इसका
तीनों भी अच्छा काम करते हैं
इसको। Your question was very relevant about critical minerals.
Sandeep Ghosh Chaudhary. I request Dr. Ghosh to come over the dais. Dr. Sandeep Ghosh Chaudhary is a professor at ACISR since 2010 and also a director NML Jamshedpur. Since 1996 he is there and he did his PhD from IIT Kanpur. He is a fellow of the Indian National Academy of Engineering and was named awarded with Metallurgist of the Year in 2015. A internationally recognized person, and he received the Alexander von Humboldt Fellowship in 2000, and he has several awards, but I am not reading all those things. But because of the short time, I request Dr. Ghosh to continue with his presentation and also stick to the time. Thank you so much.
Thank you, Professor Suresh, introducing me and to Dr. Singh and Aarti and the whole organizing team for inviting me to be here at ISM Dhanbad. So from today morning, I think people have heard a lot of things on these critical minerals and all these things. So I hope that I don't have to show all the slides, but the only thing is that if something comes up in your things, that whether to replace your old data in your mind, kindly do those things if you find that it is a new one. So what we are doing it here, that I am representing NML as well as the Center of Excellence by Ministry of Mines on the critical minerals at CSR NML. So these are all already been done by today morning by Professor Ganguly, that what is our things that India's climate constituents, and these are the clean energy targets of India, that how much we require to have based on those nuclear, solar, the wind, and then this EV, what is the million vehicles, and in the terms of energy storage. So I'm not going to do all those things, but only thing is that I think Dr. Rao has already pointed out that how much electric vehicle requires your EV, your rare earths, as well as for the wind energies. So these are the targets for those things, and for those rare earths, when you talk about those things, these are the various applications of rare earths. So do it from there or to bring it here only? Huh? Okay. So these are the various aspects. So the title is on the rare earth applications. So I'll be talking few of those things, not the other things also. So the term rare earth is nothing in the 18th and 19th centuries, but it has nothing to do with that neither rare nor the arts. As Professor Ganguly pointed out, that they are very difficult to extract and all these things. That's why they come up in that. But they are relatively abundant in the arts cast, and they are seldomly. And this is the global map for the. Yeah, you can go to it. So that where it is. So just keep those things. I think. So this is the reserve across the globe. India features at 5.73% across that. What is the global percentage? So that's the rare earth only, not all the critical minerals. And why the RE matters? Because of those clean energy, that 7 million tons in 2020 to nearly 28 million tons by 2040. So nearly 4 times of those things, and that's why we require to have all those minerals present to have our energy security. And for the energy security, as in the morning Professor Kumari said, energy tranquility, equality should be there, and that's what that environment sustainability as well as the energy equity also should be maintained on those things. So now out of these rare earths, these are the lanthanides, and one of the major problems that why it has been used for these magnets of the wind energies and LEVs is this AF electrons. The magnet which was developed in 1945, but presently with the rare earth, what we do those things, the last line, the tiny rare earth magnets can do the same job as larger magnets make, which are without any kind of a rare earths. So that's the purpose for which we can have the rare earths in our magnets, which is required for electric vehicle as well as for the wind turbines. So these are the things that neodymium, praseodymium, dysprosium, and the terbium. Unfortunately, we have very less quantities. Of course, IRL is there. They will tell that yes, we are making, but unfortunately, they are at very low category, low quantities. So they are also producing, but India is till date only samarium cobalt. But now I think IRL coming out from the monazite sands and getting all those things. So this NdPr alloy is being used in the permanent magnets. And dysprosium is far less abundant than the other rare earths, and its low availability may hinder the development of high temperature. Because when you talk about this EV or the wind turbines, this works 24/7, or when you have EV, it has to be very fast. I require a very fast pickup, so I to be driving fast, so the motor has to drive fast. So in that cases, there is a possibility of a temperature, and we know that all these cases EVs, it is only at the bottom of this back in from the motor or from that battery has to be properly dissipated. But unfortunately, if it is not dissipated, there is a possibility that this heat can be demagnetized, and then the whole property gets lost. So that's why these particular magnets should have some high temperature capability. So these are the rare earth magnets, and now we have put that in terms of the B values, in terms of the H values, because these are the two parameters which are more important for any magnetic materials. So our this NdFeB and SmCO2, they lies on the top corner itself, so showing that they have not only have a high H values, but also have a high B values, which is there in that. Yeah. So why it is required in that? You said I will talk to you with that left hand corner in that is the orbitals point. And if you go to the 4s, 4p, 4d and the 4f, you can find in the 4f there are 4 are you are filled up with 1 spin, 1 electrons, and then 3 are vacant. Similarly, for our dysprosium also, this particular thing is called as a 4F4 and 6S2, whereas the dysprosium, this is 10 and CS2. Again, there are some 4s. Like neodymium metal, there are 4 atoms are your lonars, whereas dysprosium and samarium has 5 like this. So these unpaired electrons tend to point or spin in the same directions, and that's what creates a sort south and north pole, and that's the magnetism come into pictures. And that is the purpose for which we can work, all these magnets can work as a very good magnetic properties in the power of these magnets. Now when you talk about these magnets, they also crystalline, not non-crystalline, but this is the structures. R20, R2, Fe14B, this is the hard magnetic phase. And you can find that how this, if NDFeB, how these atoms are getting distributed. So if I had some other elements, or if you have some other things, they have to replace those things. And this is not a symmetric crystal structure, that is it's called a asymmetric crystal structure, because A equals to B, but not equals to C. Of course, all the angles are alpha, beta, gamma is 90 degree, but it has a C axis, which is known as a asymmetric, or we call it anisotropic things. So when you talk about the anisotropic things, there are 3 ways. Either you use the single crystals, or you can use a sintered magnet, which is there in our Vizag plant by IRL, or there is another technique which is called as hot deformations. And being a metallurgist, we like to have the hot deformation because there you can play with that stress or the strain and the temperature. And that's where we can generate a lot of microstructures. And when you talk about the microstructures, for example, Hall pitch equation is there, where it says that if you vary the Hall pitch grain size, then your strain property you can manipulate not only the strain property but also the toughness. Here toughness is not important, but of course the strength is important, because the material should not be brittle. So that particular property which you do those things, that we have melt spinning, we have cold press, hot press, and then we do those things. Now when you do this hot deformations in those to make the product in a bulk scale, we have several other things coming into picture, which is known as a grain boundary phase, or as easy axis directions, or the compression directions. Now when you talk about all those things, there is a grain boundary phase, because when you add certain metal elements, see, don't confuse these particular arrows with respect to the spin. These particular arrows are with respect to that crystal structures of the axis, because they grow, the growth directions corresponding to the A axis of the direction. So that's why it has given that in which directions they grow when you do the hot press, or when you do the hot deformation itself. And you can see the particular images in the TEM, that how this particular grain size has been elongated in one particular direction, and that's the giving that on this basis. So what is the possible mechanism for those things? The possible mechanism, what I have done it. Next one. Yeah. So the thing is that if there is a grain boundary phase which just melts, and that allows that grain growth to occur during the hot pressing, and this liquid grain boundary phase acts as a lubricant, as a path for the transfer of atoms. So that is the grain boundary diffusion it controls, and that's the way it controls other things. And that is the anisotropic grain growth happens during the hot deformation, and that also leads to that magnetic property in these materials. Also, you have one more point. Today we can characterize the grain boundaries. We know that metallurgical engineering or any physicist, that grains are basically your periodic array of atoms are there, so they are crystalline in nature, but at the junction of those grains there is a disorder, and that's why there is no kind of a periodicity is maintained. Now we as a physical metallurgist know that because of the phase transformations, classical phase transformation theories, these grain boundaries are supposed to nucleate or allow the nucleation of any phases. Now if there is any second phase comes into picture, then there is these grain boundaries are very, very prominent, or very, very your favorable site for those. So we should not create any kind of, or we cannot allow any kind of phase transformation to take place only on the grain boundaries, because then my whole magnetic property will get lost. What you can see these things here, this is a sintered magnet and this is a hot deformation magnet. I think with that, we can go to previous one. What we can find it out that what is this red and blue, this is the magnetization and the demagnetization curve. But in case of hot deformed magnet, you can find there is a deflections. So when there is a deflection in this process, we know that there is some other process is taking place. So this magnet has two different magnetic phases. That happens in this particular things. Then we can find out that when you change the hot deformation temperatures, then you can find this particular deflection is still continuing, except at 850 degrees centigrade, which is at higher temperatures. And so it says that the shape of the initial magnetic curve will deflect the magnetic structure is also changed gradually with the hot deformation temperatures. This is a graph which shows that average grain size with respect to the coercivity, and you can find as the coercivity grain size decreases, obviously the coercivity increases. Now there are 5 alloys, A, B, C, D, E. Now you can find at the top it is a red color, that is the E. After that it is the D, that is that. See, D and E has some kind of a dysprosium. So that allows a better having porosity compared to the ABC, which doesn't have any kind of dysprosium in those materials. So that's what it is saying, that dysprosium, adding dysprosium and increasing the amount of total rare earth elements improves the porosity. And obviously in these particular things you can find the remnants decreases with decreasing grain size. This is because grain alignment requires a certain level of anisotropic grain growth. So that has to be there in that, and that's why hot deformation help us to get those properties of the materials. So this is a summation of those things, that if we can reduce the grain size, then you can find that SCL and all these things that can increase. So this is a developed, means it is a laboratory scale development, not a conventional, your marketed or commercialized. But this application of this grain boundary engineering techniques, such as the grain boundary diffusion process to the hot deformed magnets, can lead to the porosity with a small addition of rare earth elements. Now, if we can do some kind of a NdFeB, because there are other rare earths also, like your cerium and cobalt. But this is the one is that for single crystals, and you can find that the red one is NdFeB without any kind of additions. But in case of additionals, you can find the property is little bit reduced, not exactly a drastic decrease on those things. When you come to the sintered magnets, the red one is far ahead of those things, whereas the other materials, you can find that once we add, or we can replace with Nd with Ce as well as the cobalt, you can find it gets shifted to the other side. But when you talk about the hot deformed magnets, when you have only the cerium and the cobalt, then it is the blue color, which is a little bit different, but the other cases it is alright. So if you have a hot deformed magnets with additions of replacing the neodymium with cerium and cobalt, you can go up to a certain level by this kind of processing route in this material. Of course, this is not our work, this is taken from this particular paper out of those things. So this is in a nutshell that how your comparison between neodymium magnets and the samarium, because when you talk about the high temperature, then yes, it can go a little bit to the high temperature, and the QE temperature is also mentioned here, that it is a little bit higher, lower compared to that, but it can go up to that level itself. And the magnetic strength, yes, 35 to 52, and this magnet has 16 to 32 on there. And another effect is the handling of this magnet. So this is less brittle and this is more brittle. So the handling of the magnets is also important, because ultimately if you think about it, it will go to the automotive grade. So in that case, it has to be handled by the workshop people who will be working in the assembly line for those things. So this is another example for those things, that how this neodymium replaced by little bit of dysprosium and iron and boron. So you can find that the property is quite high in that respect, and that's why it can go at that, as well as similarly the operating temperature, because this windmill and other things that works across the 24/7. So if it is working 24/7, there is a high chance that the operating temperature can increase, and addition of dysprosium in that particular things raise the magnetic property, even reduce the demagnetizing property even at high temperature. And that's why there is a lot of demand for those things, neodymium, and you can find that how at various areas of applications, the various elements are there in this. But when you talk about this neodymium and dysprosium, already in the previous two lectures were there by our UCIL CMP as well as by IRL, you can find that neodymium is very, very low in that cases. So what we try to do at our National Metallurgical Laboratory Jamshedpur, that in India already we have tons of magnets available either in the defense components or in other various components. Now if you can reutilize those things, because whatever neodymium present in the ores, this is 0.02%. But when you talk about these pent magnets, there it is 29 to 32%. So 0.02 to 29 to 30, average is 30. So there is a scale up of 1,000 times. Now rather than coming from 0.02 to a concentrate, but if I get the 30% and then make the concentrate, it looks that the industry will be good that if we can use some hydrogen storage materials also, that means where you can put hydrogen inside by absorption method, and then very fast desorption also, that one also we thought of in this. These are the graphs that lanthanum, nickel and hydride, this has 1.358% hydrogen it can absorb, and at the room temperature desorption. So you don't require any temperature or any release of pressure for getting the hydrogen back from those things. What we are trying to do all these things, I am just keeping in this, that when you talk about the hydrogen is being generated at one place, and we are from the city of Jamshedpur, where hydrogen is very much required for the steel generation, iron generation. So how to transport that, how to connect these two guys, only way you can connect is that by putting the pipelines. But when you talk about the pipelines, how material will be there? We talked about being in the steel city, that it can be only made because your fuel, that is the petrol, water, everything transported by your pipes. So we thought of a pipe through which hydrogen will pass through. Now for that, we have these Zillingham diagrams, And also another thing is that when you have a hydrogen in these things, hydrogen embrittlement is a known phenomena, the toughness is also a known phenomena. So for that, you should have no inclusions. Only if you use this rare material, they can control, or they can morphology of the inclusions can be controlled, and that can lead to a good toughness of the material, not deterioration of the toughness of the materials. Today we are having a project from IREL, thanks to DC is not there. He has given the project to us to control these particular morphologies in the steel material, in the steel, so that the toughness cannot be impaired by this hydrogen and others. Also, we are working with aluminium industries. Today there is no magnesium industry, but we are working with the aluminium industries to make, because one of the projects with NML, then the IMFT, then the CSIR worked with Niti Aayog and the 3 aluminium companies, because as you said, the aluminium, your waste product, the red mart, it has a lot of scandium into those things. Now we have given the technology to Vedanta Aluminium, that how aluminium can be alloyed with scandium, and then that can be a high temperature aluminium properties, aluminium material for those things which can be required for bromos and others, and Vedanta Aluminium is going to make it commercialized on our behalf. So this is the work in a nutshell we are doing. We are doing mineral processing, we are doing metal extractions, then we make the alloy preparations, and obviously after making the alloy preparation, we are also doing the recycling, because we are trying to get back all the alloy elements which have been put into those things, and that's the way our work at our National Metallurgical Laboratory goes on, and that's the periodic table for us. The red one is progress yet to be made a mark, but the red one and green one is already we are marked. Some of them are already being commercialized, and some of them still we are looking for partners, because India, till that, I think the rare earth industries, of course the startups are coming, but not such big industries are there who can make that money from the rare earth components or rare earth industries. Thank you very much for giving me time, and thank you for your kind questions.
Thank you, Dr. Ghosh, for finishing it in timely. Your paper was very interesting and more relevant for today's scenario, but unfortunately he holds a PhD in mining, and he has got several awards and also published many papers in international and national journals, which are of very reputed value. Thank you so much, Professor Mishra. You can just start.
Thank you, Professor Nikhil. Thank you, Chairman sir. And I'm really thankful to the organizers, Professor Singh and other members of the organizing team for inviting me back to home. I'm from here, those who are not aware. I'm Professor, Department of Mining Engineering, and right now on deputation to CSIR Simper. We have here 2 of my fellow directors from CSIR, 2 of the CSIR labs. And they are the ones who are really involved in refining and extraction of critical minerals and RE. And those who are present in here, the distinguished faculty members, I can say Professor Sumanta Bhattacharya and all other faculty members, dear students, research scholars, some of my former students, now faculty. So I am really thankful to the organizers for providing me this opportunity. I will not take much of time, although 10 minutes have been given to me, but I will try to give some of my allocation to my fellow CSIR director, another director. I will just quickly scroll down. I will not talk about what has been discussed, because since yesterday things are being talked about, critical minerals, where are we, what are we doing, what policy changes have been done in the country, which way we are progressing in, and what are the various efforts which have been made in the country in terms of critical minerals. Why are they critical in nature? That has been very elaborately being discussed, so I am not going to talk about that. I will skip this as well. In fact, the applications, because these have been talked a lot. Everyone has talked about it, even this morning, since this morning, the first presentation and so on, people have talked about it. Global landscape, in the very first inaugural talk, it was very elaborately discussed. I'll just skip it because I don't want to repeat what has been discussed and what we have heard. It's not moving. I think this was also being talked about. What are the scenario in terms of the Indian context? Where are we, and what are we doing, and what's the way forward so far as these minerals are concerned? Yes, exploration. Now, the exploration and mining. Although we know the critical minerals, their criticality and their requirement in terms of the renewable energy, in terms of defense, in terms of strategic minerals or strategic applications, it's all known to us. But in terms of exploration, a lot of work has been done, but probably at some time back, we could not identify, or we could not, this critical mineral listing happened very recently. If this would have been happened maybe 30 years or 40 years back, probably our deposits or our inventory would have been a bigger one. Reason being, we have been doing and we have been concentrating on either it is coal or any mineral deposit. So if we are doing for copper, we are concentrating on copper. If we are doing for zinc, we are concentrating on zinc. But other minerals which were present, which were in the minor quantity, we were not really bothered to look at it. But now the challenge is we have got some deposits, we have got in and developing those mines. Apart from mining, the other issue is extraction, the refining. So these are the major challenges in terms of investment, in terms of resources, in terms of development of from bench scale to pallet to demo. These are the real issues which country is facing in, and the kind of investment which is required. Apart from investment, the kind of resources, human resources which is required in terms of the scientists, in terms of the research scholars. Probably that is where we need to concentrate. I'll just skip this because we have talked about it before. Yeah, these CSIR initiatives, in fact, CSIR IMT director is here, Dr. Ramanuj. He will be talking about what IMT is doing. He's got next talk probably from him. CSIR NML already we have heard about what initiatives have been taken up at CSIR NML. We have got a mission mode, critical mission project already CSIR has taken up before the country came up with national critical mission as a mission mode project. CSIR initiated the mission mode project, and these are Sikri Karaikudi is CSC MCRI, Simford. We are part of that critical mineral mission project, and we have initiated the projects which are undergoing. NGRI is there for geophysical exploration and geochemical exploration. At Simford, we are doing tapping, wherein mapping. Probably we are in the mapping, wherein we have tried to identify the presence of critical minerals in fly ash, in waste rock. These are the two which we have concentrated, and it's refining and extraction, and the flow sheet is being developed at IMT and NML. So. And I think there was talk by Dr. Masto. He is the chief scientist at CSIR Silver, who is leading this particular initiative at CSIR Silver. We know that already 7 centers of excellence have been sanctioned, and one is there. We are part of CSIR IMT Bhubaneswar. So that is the hub, and we have spoke. And there is another hub. CSIR NML, ITISM is also a hub. So these are the 7 which have come up in existence, and we look forward, as a country, we look forward for major breakthroughs and success stories, so that our self-reliance in terms of critical mineral will be achieved. These are from the secondary resources, recovery of critical minerals. Again, this has been talked about. We have also initiated the activities at CSIR. And at IIT ISM also, I have heard that they have initiated the activities, various activities. Recycling and urban mining, yes, a lot of initiatives have been taken up, a lot of startups have come up, but there are still few challenges in terms of the techno-economically viable solutions, number one. Number two, it's collection, and then the investment which is being made. So these are the major challenges. Just skipping. These are the various industries, major industries which are involved in these activities. I'm just skipping this because this has been talked about. National policies, again, lot have been discussed about it, so I'm not going to give time on this slide. But a lot of initiatives have been taken up in terms of the stakeholders, the major stakeholders, the policy making agencies from NITI Aayog, from Government of India, Ministry of Mines, and the national laboratories, the academic institutes, the industry, startups, all have been involved in. And now the ecosystem which has been developed in the country is the right one, wherein the right investment is being made, and with this initiatives, probably in near future we will be becoming what really in terms of self-reliant, in terms of the technology requirement, or the renewable energy, or energy reliance. So probably this is the right time when things are moving in direction wherein it is supposed to move in. Challenges, there are many challenges, and as you know, the first talk was on the major challenges. There are few countries which have dominance, and they are the one who are controlling the supply chain. And another term which we never heard before is geopolitical patriotism, wherein the countries have started dominating, and then they feel like they do have the resources, but they don't feel like to share it with others, depending on their will, their sweet will. And this probably now we have realized that we need to be having alternate sources in terms of supply chain, in terms of our own indigenous alternatives, let it be secondary or primary, or from the major sources which we have realized, and we are moving in right direction. So challenges, I have talked about the major challenges in terms of processing, in terms of refining. There are challenges, and these challenges have been taken up by the academic institutes, by the national research laboratories, and we are working. Extensive work is going on, and funding from Government of India, from our own internal resources is huge, which has come up, and probably with this I will come to end of my presentation, and I will thank to all the organizers, and probably my whatever time left out can be shared with Dr. Ramanaj. Thank you very much.
Thank you, Professor Vishnu. He finished in time, so I was in a very embarrassing situation how to tell him, but he helped me. Thanks a lot. And the next speaker, I think.
The next speaker is, he doesn't require any introduction, Dr. Ramanaj Narayan. I will not read his biodata. I will just tell in one simple line. He is a person with mission in his vision. The floor is yours.
Jai Jagannath, and very good afternoon to all of you. So at the outset, Honorable Chair, Sarvanagumanji, Professor Suresh, my Dr. Mishra, Dr. Sandeep Ghosh Chaudhary, all my teachers from Indian School of Mines or what I was a student, and it was the order of Dr. D.K. Singh that I have to be here and I have to follow that order to be part of this seminar. Thank you, Professor Singh, for giving the opportunity. Then another my teacher, Professor T. Srinivas, that the era when we are learning from critical mineral a lot from Dr. Srinivas. I am proud to be alumni of this great organization which organizing this conference. And I know that the moment today morning questions came that critical mineral, which is a metal is good or mineral is good, but ISM has laid the foundation that you have to always remember our Mother Earth. Mineral is the resource for the metals and whatever alloy, whatever you are making. So mineral is a right word as a student of chemistry and metallurgy, what we understood. Self-reliance is not possible without, because he is our president of CSIR who has given us the directive that what resources can have, and you can go and see in the Ministry of Mines website and everywhere, this great visionary man from the Red Fort also this year National Critical Mineral Mission was announced, and the leader was the chief guest yesterday, Professor B.K. Saraswat, and the Niti Aayog, whatever I am looking for. And this is the scenario, because I always take that nothing is geopolitical, nothing is else. We have leftover, we have to restart, we have to resurgent. And I know that our GSI, all the institutions, all the academic partners and all the ministry has come forward, and you can show these are the latest scenario, and you can see exploration type that critical mineral that earlier we were 65, but last year it has gone to 195. So everybody has coming together. The moment you will come together, success will be yours, and there is no problem that all our young students, all my friends, all faculties are there. If we are together, we are a young nation, we can do. There is no problem. We were enriching till extraction, but we have left refining and separation, and that our bark has done a tremendous job into that. Take a leap out from there and try to do it, but you have to think differently. Everybody will talk that engineering, everybody has to collaborate, but nobody will talk. Chemistry is the key. The moment disruption will come, we always left over chemistry and biology, and I can tell in a single word of whole presentation, the future disruption will be coming for the on-site mining where chemist, biologist and photo, that is the electro, photo and bio, these are the only three resources what you have to do. So Professor Mishra has given me time, so this is the right area that critical mineral and RE, whatever we are looking for, and we are proud that Singareni and our Honorable Minister has announced that already IMMT is coming with a fly ash pilot scale development at NALCO premises with a 50 kg fly ash and taking out the rare earth element, and only not magnet that already Dr. Sandeep talked about, that we have to think forward-looking and backward-looking both. We have to understand the complete value chain, recycling, start from the primary and also end from the secondary, and nothing is a waste. So sustainability, SDG, net zero and LCO is the approach. These things this is a CC corridor, what we understand. The criticality of critical mineral will come. China, forget it, remaining uncommon country is dominating the sea. If you see Chile, Argentina, and we have brought them into the picture. China has acquired, but if you see only 5 countries, that is China, Chile, Argentina, Australia, these are the numbers. I will go directly to see. My friend from CEW, a wonderful job has been done. We have to look into the reports that latest September it has been that if you want to make India as a hub of critical mineral processing, friends, we have to pass 10th class. We have left whenever we are getting admission in ISM, we always study our plus 2. Inorganic chemistry, nobody will study full. If you will understand the inorganic chemistry of the plus 2, I don't think that whatever problem is there, only fundamentals are true. How solvent processing has been done, we have to think in a reverse manner. All disruption will come from there. Because what we do, leaching, that you will accept acid hydrolysis, base hydrolysis, and what we do, the extraction, it is the similar thing. Can we reinvent the wheel and can we think in a solvent processing in a different manner? That is the question, that is the thing what we have to do. And then if you see pyrometallurgy, hydrometallurgy, and the mixed process, this is the core of all extraction process. So all the students, please go and download. It's a wonderful book written by our CEW and with Ministry of Mines. So the in between people has left pyrometallurgy. Now once again we are rethinking. Professor Suresh has done lot of teachings that his student is working with us. Now once again, whether pyrometallurgy, only you have to reverse the wheel, when to apply hydro, when to apply pyro, and this is the combination. But can that pyro go to plasma? Can that pyro go to microwave? That is the disruption, and that is the lookout what worldwide is happening. तो देखते करना क्या होगा आगे friends, this is the scenario. This is the friendship. If we are thinking of critical mineral, we have to understand the criticality of critical mineral is here. Aluminium will always come with gallium, or it will come with this. If you are going far off, your friendship get down. How to break these bonds? Whether it may be a photo method, it may be electro method, it may be a pyro method, whatever way you are taking. But the moment you will understand this wheel, I don't think anybody will stop India becoming Atmanirbhar into the critical mineral. Because your atomic size is less, your concentration is less, and the moment you will apply a right chemistry, right electrochemistry, solution will come. So if we go to circular hydrometallurgy, that today morning we have seen that people are going towards deep eutectic solvents, biohydrometallurgy. Can we add bacteria and fungi? Can we reduce the load that whenever you are grinding, can it be a solar concentration? These type of concepts will be very, very highly helpful. And can we go for organic acids? Can you use biomass-based acid? Can we use the mine-based, that whatever harvesting acid has come, if you go to a pit of Sukinda mines, can you generate that here? And that will give, you can see, rock can become powder with a small biological process, what happens in nature. But our acid is limited. We were happy, sulfuric acid, hydrochloric acid, aqua regia. Now we have to go for oxalic acid, you have to go for citric acid, you have to go for ascorbic acid, and those type of things, whatever is coming. So now I will come directly innovative and disruptive approach. Since I am a chemist, I am proud to be called a chemist, that all your resources will come from here. We use cyan 845, but we have never looked that mineral, that what that chemistry is, and that chemistry is available in Gujarat. Go castor oil. Castor oil is a big powerhouse for developing mineral additives. Without additive, whenever all unit operations you take from your mining, starting the all flotation, you will use a reagent. If you use a settling, that place you use a reagent. Without reagent, not possible. And these are the chemistry. I am not making you afraid. You don't have to synthesize. Our lab has synthesized that, and you have to do this. And when we combine a functional group, can it will selectively extract scandium out of that, which group is required. So if you take a reactive polymer, and castor oil is India is the highest producer of castor oil. We sell 90 rupees kg to China and we buy back 40,000 kg from the China as an additive, as a mineral additive. We have the power, CSIR has the power, we have 9 chemical cluster laboratory, lot of things, left and right has to come together, chemical theme and minerals, materials theme and the engineering theme, everybody has to come together. And you can see these are the structures I am showing my friend, that whenever you use any additive, please go back to a structure. It is nothing but hydroxyl group. It is nothing but carboxyl group. It is nothing but sulfur group. And only those modifications will require. Very simple +2 chemistry will help you in extraction of this center. Today, eutectic solvent. Have we, a lot of people are there in hydrometallurgy expertise. Why we have not done our own hydrometallurgical solvent? Imidazole is being placed. We will use it, we will concentrate it, but we have never reversed back. We have a solvent extraction association of India. We have an ion exchange producer in India. Have we combined together? The day we will combine together, your solvent, your process will become easy, process will become economical, and that is the disruption what I was looking for. In CSIR lab, lot of catalyst has been developed. In lot of imidazole salt has been developed. A medicinal chemistry, a food chemistry, they are doing the separation process. They are doing the membrane separation. A water chemist always do the reverse osmosis at so many places. It is us we have to apply. Some work has been carried out in the separation science at Bart. Can we translate? Can it be bigger one? Morning it was told that if you are taking in a filter, that Whatman filter paper, coat with a chemical, apply this. If you go to Canada, they are taking out critical mineral from the coal by using the filtration, a stage-wise filtration technique with a functional membranes. So those are the things you have to think. Then this is the future, that electrodialysis. When we combine, it's a, you bring everything into solution. We have to go to electroplating industry. Now, iron is becoming gold, gold is becoming silver, that whatever way you want to do, electroplating, electrodeposition. Then we have a stratification has to come. Can we create 3 metal into one solvent? That is known as a stratification. If we go to pen technology, in one solvent we do the 3 layers of system, and that has to be applied. That is the disruption required from the other fields. Then if you want to apply solar, because tomorrow on-site mining will come from solar. Today we were talking about the platinum electrode, but you will see latest development that platinum electrode is going to be replaced with ferro L1. Today morning, just now before this, Dr. Sandeep was talking. We have to think for the electrode. Why to platinum? Why not to other? This type of thinking you have to bring CO2 mineralization that will give you from soil gel processing. And this is the product that what we are talking. If combined, this is the periodic table of IML. Sandeep has shown periodic table of NML. If both will combine, we have the knowledge of almost 48 of the elements. And some of them at commercial level, some of them the basic level, and together 6 labs of CSIR are working together, that if we will combine REs together, by 3 years we have a plan to go for 72 elements of periodic table. We will have a knowledge, we will have a capacity to do it. I also congratulate Dr. D.K. Singh and the team SIMPA, the team IIT ISM for getting the Center for Excellence. We were also got one of the Center for Excellence with NML, the another center, 2 CSIR lab had got. I think in whole Center for Excellence, this is the biggest center with 13 industry, 13 education partner, 17 education partner, and later on, these are the another 6 has been joined. So right now we have 37, around 15 industry partners plus that academy, and this is the coming together. That is the critical mineral mission what we are looking for. Friends, our Director General CSIR has been kind, and when 2023 it was announced critical mineral mission, but CSIR has started the first mission pre to that was lithium from primary. IMMT, NML and SICRI together, and we are proud to tell you that we have been able to develop flow sheet of lithium carbonate from the spodumene of Amreshwar deposit, that and it has been tested in battery. Somebody was telling battery is not manufactured in India. Go and see our facility at SICRI Karaikudi, Chennai Center, and that place it was supported by Simper, and the first manufacturing facility from end to end was available. If you want to experiment any startup, please go to our Chennai Center. And once again, we must thank Saravana Bhavanji and Saraswati, because it was their dream that manufacturing of lithium batteries would come in India, and CSIR SICRI, our then Director General was the director there, Dr. N. Kalai Selvi, and we have the facility. So India is not lacking in facility. CSIR is not behind in doing that. We are running battery to battery project, mission project. Our CSIR has invested 89 crore into these all 4 projects of the mission. One is a mapping and tapping of critical minerals, and that place 6 labs of CSIR, Metallurgical, NML, IMMT, Simper, SICRI Karaikudi, IMMT, NGRI, together we are working and coming together, and we are also attaching with the other industry partners. And then a latest mission, that this is the latest mission, it is the mission director is sitting in front of me, Dr. Sandeep Chaudhary. It has been launched, SEES mission. People were talking about the recycling, solar panel, electronic/electrical waste, and air conditioner to sustainable material, and that is the SEES project. So the first project, mapping tapping, mission director is IMMT. Battery to battery, mission director is SICRI. Then lithium mission, it is from IMT. At that place, lot of help has come from Dr. Srinivas. We appreciate during the review that whatever things we have been able to develop, and this SEES mission is being led by our CSIR. So we are working together, and I hope, I am confident that we will be able to do. And this is the analysis of CSIR, that where we are both in primary, secondary and tertiary, and out of 30 elements announced by the government, 19 we have the capability, and we are going to expand it further. And then RE concentrate from secondary, I already told you, Fly-Ash pilot plant with a supervision of Niti Aayog is coming at Nalco at the 50 kg, and already installation has been started. This place you will find Sarvana Bhavan also, Red Mud, IMMT, NML, Dr. D.K. Singh was also there, and we have released the report with 3 flow sheets developed together, and 3 industry and 3 academics, JNRDC, NML, IMMT and Nalco, Hindalco, Vedanta, together we have done, and 3 flow sheets have been reached out, and the pilot scale that economic activity is carried out. Once again, it was the directive of Niti Aayog, the combination of Saraswati and Sarvana Bhavanji. And we will make you proud, Sarvana Bhavanji, it will come, and if India has to produce red mud based system, please don't bother about economics. Whenever we talk about economics. Out of 10 kg, you will get 10 gram. What will be that 9 kg is doing, and that place we are always bothering that making bricks. Everybody makes bricks, but nobody makes functional bricks. You have to think, all the younger people have to think that whatever is the spent amount, remaining amount, that has to be used in a cost-effective manner. You cannot compete with 2 rupees brick. Village people also make brick. The other people also make brick. But the moment you will make floating brick, CO2 absorbing brick, cooling brick, heat change brick, There is a 27 types of bricks are available in the world, and all the students and new faculty should think into that direction. Ramappa temple of Telangana is having floating brick. That knowledge is there. Why not be made? Nal Neel has made the floating brick in Ram Setu. Why we cannot make? So this is the challenge we have to make. We will import the high temperature brick that whatever is used in liner and all this system, but you have the potential, you have the opportunity. Only red one will not give you. Only fly ash will not give you. Other waste is there that can you make line? Go back to your grandfather chemistry. All the houses were not of the cement based system. Chuna, good, ये सब मिला के बनता था. That we have to relook into. That disruption has to come into the picture. And then RE compounds we have done. NML has the expertise. So in India, NML or iron, if two system is there, I challenge, because BARC is our leader, because they are in the strategic sector, but in industrial sector, if they will not do, nobody will able to do. That proud we have, that facility we have. So these are the things that whatever I am telling, these are the used by industry. These are the our technology which has gone. If you want to experiment with polymetallic nodule, we are working with Ministry of Earth Sciences from last 40 years. At the Center for Excellence, the real person, I am here just like his statue, but it is being done by Dr. Kali Sanjay, the hydrometallurgy head. He has done a tremendous job and very high energy. So all these activity and Center for Excellence, he is leading, not I am. As a director only I have to give him support. These are the plant. I am telling, no, I am not talking, so this is a proof. Then marine sources, we are the champion. This is the level of technology, whatever you are talking, deep sea mineral, chromite, black mass, marine chemical, low grade copper, all the TRL level. So we are there. If you want to learn, if you want to experiment, you are most welcome here. Dr. Suresh, a student, he was talking about Dr. Angari. We are proud of his contribution that IMMT is going to have the country's first PGE 5 ton per day processing plant at pilot scale that can as a manufacturing. It will be operation from the January 1st. Almost 70%, and it has developed from the chromite reject. The second, already I talked about the lithium ores. Once again, Angari and team had worked there. So we are not limiting to Amreshwar. We are targeting Riyasi. We are targeting the hard rock from the Dagana, Rajasthan. We are targeting the Jharkhand, that mica belt. We are targeting the Chhattisgarh. Whatever samples we are bringing, something is responding, and that place disruption is coming. Riyasi deposit is not coming from a normal flow sheet basis, but that place, once again, first pyrometallurgy, then hydrometallurgy, other place, all your normal processing state, and that is the disruption what you have to look for. This is my area of research. I am proud to be a polymer man, and I have, if you go to my publications, almost you will get 90 papers on these two things. And this is the things what you are looking for. Hyper branch polymer. Today we are looking for deep eutectic solvent, ion exchange resin, this additive. But if you are not looking, in the UK side, they are working on water-based system, which will settle your mineral in that aspect, and that place, hyper branch polymer is coming into picture. With a OH group, you can create wonders. And this is the sol gel, friends, I told, it was a physicist chemistry, now it is a chemist chemistry. You have enormous innovation potential to do that. And these are the things, whatever our group has done, and this can be used into the mineral additive. Then, this is a water-based system, that is a silica-based. Each, with a generation, whatever I want to track, I can do sulfur, I can do phosphate, I can do carboxyl, I can do amide, I can do epoxy, any catcher with an ease of modification you can do, and it is a one-pot synthesis you can do into your level. But that's why you have to become my friend if you want to extract. Then this is the castor oil. Once again, IICT, where I was there before, our group has published around 40 papers on the castor oil exploration, and already 3-4 are in the industrial. That floor coating of Dhanbad Chemical Pune, that was developed by our group. It has been given to do. If you are going to Berger paints, polyaspartic coating developed by us, and those technologies now I am bringing to mineral additive, and that's why Dr. What is called? Okay, I will tell later. And this is a fundamental, double bond I can make easily. Hydroxyl group, this is the only oil in the country or world which is having hydroxyl. And that hydroxyl group gives you benefit. Double bond can be created into hydroxyl. It can be created with a carboxyl, you can put into water. So we do at IICT, or even now I'm empty, I have a full-fledged lab, and that place I do everything from solvent to water. Okay? So these are the innovative steps, disruptive approach. We have to think, you have to become friends with a polymer. You have to friend with a biologist, because I have not shown you phytomining. Why we are not thinking of phytomining? Why we are not putting the biological system? You will go to northeast, there is a legume that in the tree green patina is coming, that will only extract nickel. Now you will see nature paper, maximum paper is coming into phytomine. Whenever we fill the mines, we can extract from the top. And friends, you have to do with a different lens. Primary is, if it is there, it is good. Look for secondary, look for tertiary. If you will come with me to Jamandova, all coal mines, all dust you collect, take a lens, make a solution out of the surface dust, you will get critical. 100% guarantee. Take a chemical reagent. All of you who has passed in organic chemistry, any student can tell me. We used to do radical test into our class. 8 radical identification. And some teacher will come, it will react, your paper will become wet. That was the critical. Interfering radical, interfering separation, go back to Vogel quantitative analysis, and you will get back to the what is required critical mineral. So now chemist and biologist role. Open your eyes. Your lens should be different. आपके घर में mobile uses 83 elements. Your printed circuit board that Dr. Sandeep was showing, it is having gold. अब हर लोग घर में like alchemist novel, you have to make everything out. So all my dear friends, all the faculties, put a small furnace with you, mix, do whatever experiment, disruptive experiment. I put at IMMT, अरे कुछ नहीं होगा, रेड मट ले लो, प्लाज्मा लगा दो. Do the characterization, do some solution, how to bring into solution, how to put the heating source, and that is the trade of the tricks. We have been, all of you have taught us. If you are doing right chemistry of class 10th and 12th, I am telling India will be mixed that whatever our Prime Minister is looking for. And our Indian School of Mines or IIT, ISM, today, what is the first line of our logo? Utistha Jaga. Utho, Jago, and critical mineral will be over. There is no geopolitical. It is our mind block. We don't have to read statistics. We have to apply our brain. कोशिश करने वालों की कभी हार नहीं होती. इसलिए हम लोग करेगा. BARC has generated the knowledge. IIT, ISM has spread the knowledge across the globe, and CSIR has developed the technology. My friends from Center for Excellence, you do from TRL 1 to 3. Come to TRL 4 to 7, NML is there, IMMT is there, Simfer is there. bit simple, right? Moscow will be there somewhere. It is there. Now we are trying to explore coal. And the moment we will do, Hungary has done from 2 ppm. With Mintek South Africa Organic Odisha Mining Corporation, from 2 ppm we were able to get PG. Where is the challenge? Lithium, so much less resource. One trick was told by Dr. Srinivas. We have been able to develop battery grade. We have not only go for that, we have developed around 99.9% purity, and that was further become battery grade by Sikri Karaikudi, and it was tested into cell, that lithium carbonate battery grade cell, and that has been made. Nickel, we have to go to Sukinda mines. So now I have personally visited by car each district of Odisha. Even Jharkhand, I came to Dhanbad and all the places. It is a gold mine. It is a startup ecosystem we talk. This is the startup ecosystem. And critical mineral can create millions of startups if you think right. Don't go for critical mineral, Sarvana Bhavan will sell, or strategic sector will take. But the reminder, out of whatever PG we are making, it will come 1 ton 10 gram, remaining 9,999. At that place, apply the combination of best, that is the disruption required. Same coal fly ash, now it is coming FGD technology to reduce the height will be reduced, FGD, and that place they put lime will come out, calcium carbonate will come out, combined redwood with not only fly ash, combined with that, heat it. Heating is a solution. Disruptive mixing is a solution. And experiment with your hand is solution, not with your contract worker and with your labor. And then you will able to develop technology. That is the trade of the trade. Once again, thank you for giving the opportunity. And sorry for taking over. Thank you.
Sir, thanks for the wonderful lecture. Actually, in the beginning itself, I told you are a man with a vision in your mission. I think you have justified your presentation based on that. And I think you have not spoken about MMT, you have spoken about all the CSR labs. That is the fundamental thing which you should note, because he has encompassed all the CSR labs together. That itself shows the spirit behind the presentation. And rightly, he is heading this 4M mission also, mining materials, metals and materials. I think he has not touched upon it because it's a Bible on its own. So thank you, thanks a lot for the presentation, sir. For doing the honors for the 3 CSR directors, I request Dr. T. Srinivas, former head, Metal Divisions BRC, to come to the stage, please. So I request all the 3 directors to come over.
IMFT, earlier it was 20 channels. Due to RE, now we are establishing 207 pilot plant systems. Anybody want to do molten salt electrolysis pilot plant, that is there. Another pilot plant is coming at our Enable. That magnesium, although it is not listed into critical mineral, but from the fission process, we are developing 1 pilot plant at Enable. So a lot of pilot plants are coming. And then for recycling, Enable is having 1 pilot plant, another pilot plant is coming at IMFT. So let us explore together. We are not divided, we are a mineral community, metallurgy community, let us work together. आप जहाँ खड़ा होंगे लाइन वहीं पे शुरू
We extend our heartfelt gratitude to all the speakers for sharing their decades of academic and industrial experience. I believe we have all gathered valuable information that we'll be carrying with us and hopefully applying in the future.
We also thank our chair and co-chair for guiding this enlightening session. May I now request Dr. T. Srinivas, former head of Mineral Division, BARC, Hyderabad, to felicitate our chair and co-chair with a token of appreciation.
All the concentration. May we have a huge round of applause.
IISM Dhanbad would be provided with their certificates later.